Hello, everyone. Welcome to the November 2021 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. Still reporting to you from my sabbatical in Boston, Mass., where I'm visiting Harvard. It's been fun seeing people I've known for a long time, catching up, getting a little bit of science done collaboratively, and also meeting some people who I hadn't already known. But I will be honest, most of my time has been spent trying very hard to finish up this book manuscript that I'm working on. So it's been a lot of alone time in that sense. As some of you know, I did this video series last summer on the biggest ideas in the universe, and I'm turning those videos into a series of books, 3 books. So I just finished up the manuscript for book number 1, or almost finished. I shouldn't curse myself there. I shouldn't jinx myself. The first book is on classical physics, the second one's on quantum physics, and the third one is on miscellaneous topics, largely about complexity and emergence and things like that. Classical physics, of course, includes general relativity and space-time, black holes, things like that. The whole point of this book series is to do more or less straight pedagogy, which is usually not what I do. Most of my books, I try to stake out some terrain that people can agree with or disagree with, rather than just telling people things that we already know. But the gimmick here is that we're doing it with the equations. So it's intro physics, but with all the equations there, including, Einstein's equation for general relativity. So I have to explain what tensors are, what the Riemann curvature tensor is in particular, what the metric is, all of that stuff. I have to teach you calculus, at least enough to understand the equations, vectors, tensors, what have you. And that's challenging. It's hard. Like, I'm looking at what I'm writing. I'm like, oh my goodness, are people really going to read this? I think some people are. I hope some people are. Some people seem to like the videos. I can explain more in the book than I can in the videos. And certainly the explanations are a lot more carefully thought out, let's put it that way. But it's still just kind of crazy ambitious to imagine that while reading chapter 2, people don't know calculus, and by chapter 8, they're constructing the Einstein tensor for general relativity and understanding the energy momentum tensor and so forth. So it's an experiment. We'll see how it goes. I think that there's only 2 analogous books that have ever been tried that I'm aware of, both, by the way, by previous Mindscape guests. Roger Penrose wrote, of course, The Road to Reality, his big old magnum opus, a very, very long book, which was originally how I thought of the biggest ideas in the universe until we decided that splitting into 3 would make it a little bit more user-friendly. And Penrose also goes through an enormous amount of details and equations and so forth. The difference is, I think, it's weird. The difference is I'm trying to be mainstream. I'm not talking about speculative stuff at all. So I'm not talking about extra dimensions of space or the origin of the universe or anything like that. I'm just talking about the ideas in physics that are fairly well established and we know. And mostly Penrose talks about that also, but he does so in his own idiosyncratic way. He's a genius mathematical physicist, but he has his own slant on things, coming largely from a GR point of view. And so I'm really just trying to let people in on how most theoretical physicists think about this stuff. And the other example is Lenny Suskind's Theoretical Minimum books, another series of books. And Lenny, of course, has enormous physical insight about this stuff and provides clarity all over the place. But it's a more traditional kind of intro physics kind of thing. So he's really trying to bring people up to speed enough to be physicists, whereas my goal is not to make people into physicists. It's to make them understand the concepts. And there's a gap there, right? There's a difference. If you want to be a physicist, you got to just get the textbooks and do the problem sets and learn not only what the equations mean, but how to manipulate them, how to solve them. It's one thing to understand what all the symbols in Einstein's equation mean. It's another thing to be able to solve Einstein's equation in a particular regime, or do an approximation scheme, or put it on a computer, or what have you. So Suskind's approach is more just intro physics, whereas mine is leaping ahead. So I'm doing things on black holes and quantum field theory and so forth that he never gets to in his books. So I think it is different. Hopefully it will be accessible to some people. Explaining tensors is not easy. Explaining the Hamiltonian formulation of classical mechanics requires partial derivatives, which involve funny symbols. I do think that just the funniness of the symbols is a big thing, right? I mean, The existence of Greek letters when you do tensors in space-time can be extremely intimidating, and for good reason. If it's an I and J, K, then at least we've seen those letters before, where if it's mu, nu, and lambda, that's an extra layer of intimidation that the symbols get you. But it shouldn't be, from a purely cognitive point of view. They're just symbols. Who cares? But, you have to understand that when you say, okay, this D in this font means ordinary derivative, and this sort of curly-looking D in a different font means partial derivative, and that has to do with when you have more than one variable, you have to sort of acknowledge the fact that that is intrinsically intimidating or hard to instantly grasp, even if the underlying concepts are actually not that hard. So, I'm constantly trying to put things into context, make it easy without going at, tremendous length, right? I mean, I want to keep everything compact enough that you can swallow it in a reasonable amount of time, rather than just doing a million different examples and things, doing enough examples to get the point and then move on quickly. Again, we'll see. I'm talking about this because this is what is on my mind right now, trying my best to make the biggest ideas understandable to everybody. Anyway, this is this month's Ask Me Anything episode. As always, the Ask Me Anything episodes are brought to you by the people who are contributing to Mindscape via Patreon. If you would like to be such a person, you can go to patreon.com/Sean M. Carroll and chuck in $1 or $2 per episode. That would be wonderful. The Patreon supporters are great for many reasons. They bring us not only these Ask Me Anything episodes, they get ad-free versions of the episodes that they can listen to. And they also basically are paying for other things like the transcripts that we get of every episode. So there's transcripts both of the AMA episodes, but of literally every episode of Mindscape. You can get transcripts at preposterousuniverse.com/podcast. So if you want to search how many times has he mentioned renormalization, or some guest has mentioned something like that, or the hard problem of consciousness, you can find all that at preposterousuniverse.com/podcast. We built up, it's been over 3 years, built up a big backlog of people talking about interesting things. So let's add to it and let's go. Paul Hardy says, when I studied psychology, I learned of a phenomenon whereby rats were taught new tasks that took a certain amount of time to learn. And as time went on, rats in other parts of the world learned these new tasks at a statistically significant faster rate. I know physics would say there's no signal that could account for this, and I've never found a good answer. Do you have any wisdom on this? So the idea is someone somewhere teaches rats how to do something, and somewhere where presumably it's different rats, they started learning faster. So one hypothesis, which you might write down, is that rats share sort of collective consciousness, and the minds of rats across the world share information about how to do tasks. That is a hypothesis. There's another hypothesis that says that the result is just wrong, that it was a mistake or they lied. That's a hypothesis. There's a hypothesis that says that knowledge of the psychology experiment was shared around and people thought about it and they became better at teaching the rats. That's certainly a hypothesis. There's a hypothesis that it was just the statistical fluctuation, that even though statistically significant, what that often means, especially in psychology experiments, is 95% confidence or maybe 99% confidence. And in the real world, 1% and 5% unlikely things happen all of the time. So of these hypotheses, I would say that the ones that violate the laws of physics as we know them, which include the minds of rats sharing information around the world, is the least likely of all of those. It's very, very, very unlikely. And I understand why I picked this question up because I have any special knowledge about rats or insight into psychology experiments or anything like that. Remember that I pick the questions to ask. I don't answer all of them, but if I have something that I think is interesting to talk about vis-a-vis the question, then I will choose it. So in this case, it's the fact that, all these individual alternative explanations seem a little fudgy, right? Oh, there was a mistake, there's just a statistical fluctuation. They rub us the wrong way. But changing the laws of physics to give rats telepathy should be just enormously low on your list of plausible hypotheses for something like this, because we have so much knowledge about how physics works, and but pretty good knowledge about how rats work, and none of this is very likely. So even though the alternatives all seem a little bit, you're reaching a little bit, it's nowhere near the amount of reaching that you need to do to really change up the laws of physics and the laws of rats. So I don't know what the correct explanation is, but this is a general feature of reasoning about these weird claimed studies. I mean, I don't know the studies you're talking about. I don't know if you could produce a reference to them and so forth. I should say there's a whole nother hypothesis, which is that the study or the result that you're remembering or you're mentioning, if you were to dig into the actual study, isn't nearly as impressive. Sometimes these studies, these crazy results get amplified a little bit in the game of telephone that constitutes people sharing things like that. I mean, it would be enormously great to discover something like telepathy among rats or collective communal consciousness. And it's provocative, and therefore people share it and go, what about this? That doesn't mean you should provide any credence to the possibility, really. I'd put it at about 0.00001 or something like that, my personal credence in that hypothesis. Daniel Jansen says, as I understand Heisenberg's uncertainty principle, it is only a statement about the variance of two complementary variables in repeated experiments. An experimental setup that results in low variance in one variable has high variance in the other. Are there no implications at all if you measure first, say, the position and momentum on the same particle? Yeah, there are absolutely experimental implications for measuring the same particle, and that, in fact, that's where the implications are most obvious, most dramatic. If you take literally the idea that you're measuring the position of a particle and you measure it very accurately, then after the measurement, you know strictly nothing about its momentum, because a localized quantum state, let me say it this way, a quantum state that is localized in position is completely delocalized in momentum, and vice versa. The states that have small variations in position and momenta simultaneously are a different kind of state. You cannot have a small variation in one and very small variation in one and also very small variation in the other. So the Heisenberg uncertainty principle is a statement about how quantum states relate to observables. It's actually not a statement about measurement or experimental results at all. It is a statement about how quantum states relate to observables. And we can make the statement very, very crisp and clear if you think about spins instead of position and momentum. So just like position and momentum are complementary variables in the Heisenberg uncertainty principle, so are the spin in the z direction and the spin in the x direction, okay? So it's kind of hard to visualize sometimes or to grasp, but in Hilbert space, in the space of all possible quantum states, a spin in one direction, let's say spin up, is perpendicular as a vector in Hilbert space to spin in the other direction, which is spin down. And the reason why that's hard to visualize is, of course, we think of the little axis, spin up going up and spin down going down, and those are parallel to each other. Up and down are parallel, even though they point in opposite directions. But as states in Hilbert space, they're perpendicular to each other. That's why we say that a particular spin can be in a superposition of spin up and spin down. It's the two different possibilities, spin up or spin down, okay? But that's along a particular axis. And so consider a spin. So its vector in Hilbert space is in a little two-dimensional plane. The x-axis is, let's just say the horizontal axis is the spin-up axis, the vertical axis is the spin-down axis, and the real vector is a little line segment of length 1 pointing from the origin to somewhere on that plane, okay? So you can imagine orienting that line segment along the horizontal axis, and then you say it's spin-up. You can imagine orienting along the vertical axis, and you say it's spin down. You can imagine orienting it along somewhere in between, and then you say, okay, it could be either one. And the uncertainty principle says that if you have, well, it comes from the fact that if you, instead of that spin along the, let's say that was the z-axis story that we just told. Horizontal axis is spin up along the z-axis, vertical axis is spin down along the z-axis. Then the spin x axis, the x spin description is rotated at 45 degrees, okay? So spin up along the x-axis corresponds to an axis in Hilbert space, which is at 45 degrees. It's in between the spin up on z-axis and spin down on the z-axis. You take the two axes, spin up and spin down at right angles, you rotate them by 45 degrees. And now you get spin up along the z-axis, along the x-axis, and spin down along the x-axis, okay? So the point of all that is that going from one observable, the z-spin, to the complementary observable, the x-spin, is a rotation of the axes. And the same thing is true in position and momentum, although it's more complicated because they're infinite dimensional. And the uncertainty principle is just the statement that if I just consider the z-spin, I can orient my quantum state so that it's entirely along spin up or spin down, or it's halfway in between. Likewise, I can do the same for the x-spin. I can orient it so it's entirely along spin up x or spin down x. But because those two sets of axes are rotated at 45 degrees with respect to each other, there's no way that I can have a quantum state that is perfectly aligned with spin up in the z direction and spin down in the x direction. In fact, there's no way I can align it so that it has a perfect prediction that is both true for x and z anyway, in any possible direction, because the two axes are rotated with respect to each other. That's the Heisenberg uncertainty principle. The uncertainty principle is just saying you can't simultaneously localize a quantum state along two complementary observable axes because they're rotated with respect to each other. And notice that I didn't make any statements there about observables or measurements or experiments or anything like that. Observables I did, sorry. Measurements or experiments I did not talk about. So Eric Chen says, I'm going to group two topics together, two questions together. Eric Chen says, what are your thoughts on long-termism, the view that positively influencing the long-term future is among the key moral priorities of our time? Relatedly, what is your take on the effective altruism movement, which many people who endorse long-termism are a part of? And Henry Cooksley asks basically the same question. What are the best arguments for and against strong long-termism? I'm not quite sure what the word strong is doing there. I'm not an expert on long-termism, but it's one of its pioneers was Nick Bostrom, who we had on the podcast a while back. We did, of course, the idiosyncratic thing about mostly talking about the anthropic principle rather than talking about existential risk or superintelligence or anything like that, but it was a fun conversation. And, these perspectives of effective altruism and long-termism come out of a particular kind of consequentialist moral outlook, okay? And a version of trying to be rational in the face of a consequentialist moral outlook where you're trying to maximize something. All the good experiences that people have throughout history. Let's maximize that, right? It's a sensible thing to imagine trying to do. Now, as you know, as I said before, I'm not really a utilitarian. I go back and forth. I'm not really a non-utilitarian either, and I've said it before and I'll keep saying it. I have not settled on a once-and-for-all favorite way of thinking about consequentialism versus deontology versus virtue ethics, etc. I do have a podcast coming up with someone who is a utilitarian and is in favor of effective altruism and made some very, very good points. So look forward to that soon. But I'm not myself. I have worries about it. On the other hand, there's I guess what maybe is weak long-termism or weak effective altruism, which is obviously perfectly sensible to me. Given that I would like to be an altruist, I would like my altruism to be effective. That sounds pretty good. I'd rather be effective than ineffective altruism. Likewise, I think the long term matters. I'm not in favor of taking wild risks that could end the existence of life on Earth within 100 years. That sounds bad to me. I think that people who exist in future generations should also count. So that's kind of obvious and simple. But I also think that there's a mistake that we can make and this is a mistake many utilitarians make in my view. They would say that it's not a mistake, obviously, but it's to count the lives and experiences of people elsewhere and at other times equally to how we count our experiences of myself living now, other people near to me, and people I know, etc. It seems parochial and selfish to say that I should count people near to me in my moral calculus more than people far away from me? Why does the life of someone who I happen to be looking at right now count more than the life of someone across the globe, right? But I think that there are paradoxes that come up if you don't take that point of view. In economics, for example, we always discount the future. We count individual considerations for individuals in the future less than for the present day, in part just because we can't predict them very well, right? Our effects are harder to know when they're applied to faraway lands and faraway times. So it's perfectly rational to discount in some sense. And in fact, I don't know if anyone has ever made specifically this argument, but there are versions of arguments against utilitarianism, which try to point out how counter-rational it is to really be a perfect utilitarian. And I think that what it comes down to is the impossibility of finding a well-defined measure on infinitely big sets, right? If we count potentially an infinite number of people, and we count all of them equally, then literally the only moral thing to do right now is to try to prevent the heat death of the universe. And I don't think that's true. I don't think that should follow from any reasonable moral starting point. So I think that it probably, compared to what we actually do in terms of being good human beings, governments and corporations and influential organizations trying to affect the future of the world, I think we should probably be more long-term than we are, right? I think that people don't put a lot of effort into thinking about the future. And I think that the sort of bare thing of preserving the human race, stopping us from going extinct, that should be a very high priority. But beyond that, I think that, so compared to what we actually do, it would be in favor of more long-termism. On the other hand, I don't want to take this extreme view that just pretends that everyone counts equally, every time counts equally, and we should adopt our present strategies with that in mind. I don't think that quite fits together, in part because of this uncertainty, like I said, and in part because of this fundamental flaw in utilitarianism. So, put it this way. Consider two possible futures for the human race. In one future, we figure out the work week and leisure time and basic income for everyone, and we have 1,000 years. Maybe 10,000 years if you really want to push it. But, we have some number of millennia where everyone is happy and everyone is healthy, given the contingencies of life and unpredictabilities, et cetera. But everyone basically lives a good life. They can pursue their passions. They're free from constraints of scarcity and hunger and all that stuff. They get good educations. They learn to live together. But it only lasts 1,000 or a few thousand years. The other one is we last for, a quadrillion years, 1,000 trillion years, right? With trillions and trillions and trillions of human beings. But they all live in squalor and misery, right? And you can pump up the numbers to be whatever you want. Given utilitarianism, given the fact that we're just maximizing something, utility or number of happy moments or whatever it is, you can always find a large enough number of miserable people that you get more utility out of that than a small number of happy people. That's the fundamental problem with utilitarianism. You can always win just by adding more people to the game. And I think that's wrong. And it's not like super obviously wrong, don't get me wrong. But I think that a short-term future where people truly flourish, I would say, is actually preferable to a long-term future where people are basically miserable. And I think that the straightforward, naive, long-termist calculus would disagree with me on that. So I haven't, I babbled on about it just now, but I haven't really put a lot of thought into this. I think it's important to be talking about these things. I think that the overall lesson is that there's a certain amount of epistemic humility that is required when you're calculating things of the form x times y, where x is a number much, much larger than 1 and y is a number much, much less than 1. So when you take a very big number and multiply it by a tiny fraction, this is always the game that is being played by these very long-term calculations. Well, if there's a 0.001 chance that humanity will go extinct, but there's huge damage if humanity goes extinct, right? That's the kind of calculation that is done. And you say, well, we should forget about climate change and poverty and disease and war and try to go from 0.001 chance that humanity will go extinct to 0.0001 chance. Hope I said that correctly. But so I don't buy that. I do not agree with that kind of reasoning, because I think that there are generally error bars on those numbers that you're talking about that kind of wash out all the effect. Same thing is true for Everettian quantum mechanics when you're talking about these ridiculously unlikely branches of the wave function, right? People really focus on these because they don't like the implications. But don't focus on these really unlikely things in these calculations. I think that our uncertainties about those should be very large, and they should not drive our fundamental decision-making processes. That would be my short version of my unconsidered take. Linnea Miziara says, David Albert said that when an amoeba splits, it doesn't really make sense to choose one of the descendants as the real one. You've said that in many worlds, when we split, the destiny of our copies doesn't really matter to us because they will go on to live happily, entirely independent lives from ours. He didn't say happily, sorry, just entirely independent lives. However, doesn't that imply that we are choosing one of the copies as the real myself? Isn't that just like choosing one of the descendants of the amoeba? No, it's not at all like that. The point is that there are many future copies of me. Each one of them should look out for their own interests. Likewise, if you take some past version of me, I am one of the descendants of that past version. I should look out for my own interests. There's nothing I can do that affects what's happening to the other copies of from my other descendants of my past self. That doesn't mean I'm special. To them, they're special, just as much as I am special. No, there's no godlike view that is pointing out any one of the copies as more important than any of the other ones. Mark Kark says, is there any physics prediction for what existed before the Big Bang? I wouldn't say prediction. I mean, literally, it can't be a prediction for what existed before the Big Bang. It's in the past. But there's scenarios, right? I mean, the amount of knowledge we have, or even confidence, high credence scenarios is very, very small. I wouldn't put too much weight on any of the scenarios that we have. But it's possible that nothing existed before the Big Bang, by which I don't mean there was something that existed before the Big Bang called nothing. What I mean is there might be no such thing as before the Big Bang, right? I mean, that's probably what is the traditional view of the Big Bang, that it is the beginning of time. It's also completely possible there was a contracting universe that bounced. It's also completely possible there was a more or less quiescent universe that somehow bubbled off a universe like ours. There's many different possibilities to it. I do think, let me just take this opportunity to say, I think that not enough brain power is put on considering the possibility that the Big Bang was not the beginning and it wasn't a special event either. A lot of scenarios that try to invent a picture for what space-time could have been doing before the Big Bang make it either like the mirror image of our universe, some contracting universe or something like that. But it could have been a completely different kind of thing. It could have been, like I said, just quiescent empty space-time, which is the scenario that I put forward with Jennifer Chen, or it could have been something just very radically different. Even the people who'd like to think about time before the Big Bang still want to attach some specialness to the Big Bang. That's a sort of natural move to make, and I think it's not necessarily the only move we should be thinking about. All right, I'm going to group two questions together. Let's see if I can remember why I grouped them. Joseph Williams says, do you ever think that's too much information to be a coincidence? For me, the fact that the chemical makeup of stars and their distance is communicated via light across the universe seems more than just happenstance. Seems there's too much information suggesting something more fundamental and profound is at play. Gary Upshaw says, ancient astronomers and philosophers and European astronomers were inspired by patterns of movement of the sun, moon, and planets across the heavens. From these patterns, they learned to predict eclipses, eventually to discover the law of gravity. The orbits of the moon and planets is fairly simple in a single sun system. If the system was a two-sun system, do you think humans would have advanced scientifically? Right. Now I'm remembering why I'm grouping these two things together. So both questions are about, so I would classify these as saying, look, here's our universe. Here's the universe that we know and love. Look at all the amazing stuff we've done. And if we lived in a different kind of universe, then we wouldn't have been able to do that amazing stuff in exactly the same way. Right. So Joseph is saying we get spectral information from stars that lets us analyze their chemical composition. Gary is saying that the motions of the planets in a single sun dominated system is fairly simple. That helped us work out Kepler's laws and Newton's laws and eclipse timings and things like that. So I would say this is extraordinarily ex post facto reasoning. It is of the same character as the famous claims about how, it's purported, well, it's supposed to be a reductio ab absurdum, like looking at a puddle, right? And you say, wow, look at that. The shape of the water in the puddle is exactly the same to fit exactly what is necessary to fit right into the shape that is created by the mud that the puddle that formed the puddle in the first place. Isn't that a remarkable coincidence? And of course, the answer is it's not remarkable at all. The shape of the indentation in the ground comes first, and then the water settles into that shape, right? This is supposed to be a response to fine-tuning arguments. Likewise, I would say that, whenever anyone says that isn't it remarkable how much progress we're able to make from scientific data, whether it's the spectra of stars or the orbits of the planets and the sun. And by the way, Robin Collins, who's a theologian, has tried to systematize this. He actually claims that the laws of physics are maximized for discoverability. Right? They make it easy as possible, easy as conceivable to discover things about the universe. But that's just because that's happened to us. That's because that's the particular way that we were able to make progress. There's lots of things we can't make progress on. We don't know what the dark matter is. We don't know what happened at the Big Bang, right? I mean, 200 years ago, it would be easy to come up with a list of things we didn't know. It took us a while to invent quantum mechanics and so forth. The idea that somehow scientific progress or knowledge of the universe has been made easy by features of the universe seems entirely off base to me. There's a selection effect. We're impressed by the stuff that we can discover first. If the laws of physics or the situation of the universe were very different, there's other stuff we would discover first, and we would call that amazing, right? There's no, in other words, a priori expectation for how easy it should be to discover things about the universe with respect to which we can compare our actual experience. There is something about the universe, to be fair to the other side. The universe is largely intelligible, right? It obeys rules. It obeys patterns. There are discernible patterns, the laws of physics that we can discover. Is that surprising or not? I really have no way of judging, but I get the question. In the space of all possible laws of physics, I can imagine that the vast, vast majority of them would be very, very hard to discern. So in some sense, we have locality, for example, is the most obvious thing in the world. Determinism is another pretty obvious thing. But the fact that we live in a world governed by field theory and the fields only interact with each other when they're the same point in space-time, okay? That's a huge, huge restriction on all the possible things. I could easily imagine laws of physics that would let rats communicate telepathically, the best ways to run through mazes and things like that. But we don't have those laws of physics. So that is a fact about the universe that is certainly non-generic in the space of all possible laws of physics. Is it surprising? That I have much less to say about. There could, if we're super duper ambitious, and I'm actually thinking about this, there could be a selection effect, a dynamical selection effect that uses emergence to say that when there are creatures, intelligent creatures that can look at the world and think about it, like us, that emerge given laws of physics, they will always discern more or less intelligible laws of physics. So there could, again, be some kind of anthropic selection that in the parts of the multiverse, if it's something like that, where there exist human beings, they can, or other intelligent beings, they will see simple patterns in the laws of physics. But, that's a very, very speculative, crazy idea. It's not something that we can say, oh, yes, it must be like that. Martin Dushek says, when science fiction talks about using black holes as a slingshot mechanism, where does this energy come from? If it comes from rotational energy, does this mean it wouldn't work with non-spinning black holes? Well, I don't know what science fiction stories you're talking about. So maybe they're just making stuff up. That's always possible. And maybe a better way to ask it is it conceivable to use black holes as slingshots in ways that are compatible with energy conservation and other cherished laws of physics? And I think the answer is yes, and there's at least two different ways. I mean, one way is just to use black holes in a similar way that we use planets in the real world, right? NASA and other space agencies, when they are launching probes around the solar system, will very often use what is called the gravitational assist from other planets. So you have Jupiter out there, and you can slingshot around Jupiter and use that as a way to go a lot faster. And you should ask yourself, well, where did the energy come from to make your spaceship move a lot faster? And the answer is Jupiter is orbiting the sun. It has some velocity, it has some momentum, it has some angular momentum, and Jupiter slows down by a tiny, tiny, tiny amount, completely imperceptible, but it gives a little bit of its energy and its angular momentum to your spacecraft. So there's nothing violating anything about that. And likewise, if you have black holes that are moving in some reference frame that you care about, you can borrow a little of their momentum to slingshot a spacecraft or something like that. But that could also be done with planets or stars. You don't need a black hole to do that. There is something special about black holes called the Penrose process, named after former Mindscape guest Roger Penrose. Have I mentioned that he was on Mindscape? So one of the things that Penrose invented in the 1960s is something called the Penrose process. If you have a rotating black hole, you can, again, in a similar, spiritually equivalent vein to borrowing rotational energy from Jupiter, you can borrow rotational energy from a spinning black hole. The specific way you do it is a little bit trickier, but roughly speaking, you fly near the black hole, you throw something into the black hole in the direction opposite its rotation, so you slow it down, and in response, you are kicked out faster than you went in, and the black hole slows down a little bit. And the fun thing about this is that there's a limit on it, because you're throwing things into the black hole, slowing down its rotation, and therefore making it a more and more slowly rotating black hole. And in the process, you can prove, Stephen Hawking, famously, this was I think one of his first big theorems, the area theorem. The area of the event horizon of the black hole always goes up. You can extract energy from the black hole if it's spinning, but the area of its event horizon will always increase along the way. So maybe that's what your science fiction stories are talking about. I'm not really sure. Okay, now I have a bunch of questions that are kind of groupable about they're all about personal identity in some sense. But I'm going to read them separately and try to answer them separately. But anyway, there's a theme for the next couple questions. So Lars Kruger says, do you think that the continuity of personal identity consciousness is an illusion, and how would you argue that it's not? So no, I don't think it's an illusion, but I think that the answer involves mostly a careful thinking about what we mean by illusions, not a careful thinking about what we mean by consciousness. I don't think there's anything special about consciousness. I think the continuity of not a personal identity, but there's a continuity of identity of the chair I'm sitting on, right? There's a very real sense in which the chair I'm sitting on is the same chair I sat on yesterday. What is that sense? What does that mean? I mean, it's a collection of atoms, etc., but it's at a different moment of time. I could be like really hardcore about saying that the chair at one moment is a different chair than another moment, a different thing. It's a collection of atoms at a different moment of time. It's at a different location in space-time, right? But it's dumb to be that hardcore. You could be. It's consistent, but you are letting go of an enormously useful handle that you have on the world, namely the knowledge that comes in a very compact, usable form by saying the chair that was there yesterday. It implies a whole bunch of things. I remember what it was like to sit on the chair yesterday. That's probably going to be pretty similar to what it's like to sit on the chair today. If the chair has, a wheel that is about to fall off, it's probably still true today. If I need to put a pillow on it to make it comfortable, likewise. So what we do in the real world is to group things together in ways that provide us a handle on the real world that is useful, right? We don't want to separately pretend to specify the position and velocity of every particle in the universe at every separate moment of time. That's a silly way of thinking about the universe. We can't do it. So instead we group things together. That's what emergence is all about. Coarse graining is all about. You chunk things together into groups that qualify as entities that are describing rough approximations of the specific underlying particular configuration of fundamental stuff, okay? And that's where the continuity comes from. The fact that if someone says, you know, oh, I sat on the chair yesterday, it was comfortable, that makes predictions for the future, right? It gives us a handle on the world. It predicts it'll probably still be comfortable today. And I think exactly the same thing is true for the continuity of personal identity, right? I mean, it's useful not because it's some fundamental category in the universe, but it helps us understand and talk about the universe in useful ways. If you are talking about a certain person that you know, a friend of yours, and you say, well, you know, they're always very persnickety about what they eat, okay? That provides you some useful information about how to feed them and how to treat with them if they come over to your house or something like that. So that's the sense in which personal identity is not an illusion. It's real. It's continuous over time in that sense. And I can make it first person if you want. You know, when I say that I ate too much yesterday, and that's predicting and explaining certain features of my feeling today, right? That's exactly what is going on. I don't think it's anything spooky, anything fundamental. It's a higher level emergent reality. But that's very, very different than being an illusion. An illusion is something where you think X is true, but X is false, right? And a higher level emergent thing is very useful and true. An illusion is when the magician pulls a rabbit out of a hat and it makes you think that there was no rabbit there and he made a rabbit appear. That's an illusion. But the continuity of personal identity over time is not an illusion. That's a very real thing. All right. Matisse Remakers says, a priority question. Remember, priority questions are the ones where you can ask them and I will do my best to answer them. I won't answer everyone's questions, but for every person who is a Patreon supporter, once in their life, gets to ask a priority question, and then I will try my best to answer that priority question. Now, the problem is, you know, if you don't like my answer, you don't get a do-over. So it's an AMA. This is not a truth service or I promise to give you satisfaction service. This is, you can ask me a question, I will give you an answer, and then you have to deal with the answer. So with that in mind, Matisse's question is, the thought experiment here below is giving me a headache, and seems to imply that assuming functionalism, infinity of space, and finite dimensionality of the Hilbert space of a human brain, any first-order perspective is in a sense non-local. Please have a shot of debunking it. I'm building two identical conscious robots that run a deterministic programs, and I place them in two identical rooms, room 1 and room 2, both with a single door. On the outside of each door, there's a plate with the room number. Now I turn on the robot in room 1, tell him he's in room 1, and let him explore without opening the door. After some time, I turn the robot off, copy its memory banks perfectly to the robot in room 2 with a memory stick, update the position, etc., turn the room 2 robot on. From the robot's perspective, nothing interesting happened, and he would only be surprised to find himself in room 2 after opening the door. You might argue this robot only thinks he's the same robot in room 1, but his feeling of self meets the same standards as those of you calling yourself of several days you. At least this is what functionalism assumes. Now I repeat the experiment. It's a long question. Sorry, folks. But instead of only switching on the robot in room 2, I switch on both robots simultaneously. And I tell them the trick that I pulled. Now both robots will be unable to tell me with certainty in which room they are. Does this mean that from their perspective, they are either the robot in room 1 or room 2 and they just don't know, or they're in a sort of limbo of which robot they are? While the first option seems intuitive, it implies that somehow during the copying, a choice was made, but the data on the memory stick is always the same as in the first experiment. If the choice was made when the robots were turned on, why not 10 seconds after they were turned on? The alternative seems to be a sort of limbo until they open the door, which itself sounds ridiculous. So I think there are two things, 2 points I will make. I'm not sure if I will offer a satisfactory, complete answer to the question, but 2 points I can make with some degree of confidence. One is that all of these kinds of duplicating, transporting, teleporting experiments give us philosophical trouble because they never happen in the real world, right? We have no experience of being duplicated and held in a room. So all of the ways we have of talking about personal identity, as we were just talking about, all of the reasons for which it is useful to talk about who we are in the world, et cetera, and attach some identity continuity over time, are predicated on our actual experience of the world, in which these duplication experiments never happen. So it shouldn't be surprising, is the first point I want to make, that when you violate the things that actually we're familiar with in the real world, you come across situations which don't fit comfortably with our categories, okay? So we don't have a right to demand that the categories we invent for certain circumstances always make perfect sense and fit perfectly comfortably with new circumstances that we're considering. That's point number one. Point number two is that there is something about this experiment, room 1 and room 2, that exists not only in the minds of the robots, but in the minds of the outside world. We're allowed to, if we're considering what is true and good about the world, think about the whole system and its relationship to other things. So the short answer, I think, is that there is absolutely a fact of the matter about which room the robots are in. There's a robot in room 1 and a robot in room 2. I think there's zero ambiguity about that. Now, you can put into the robot in room 2 all of the memories and impressions of the robot in room 1. Sure. And then I would just say the robot in room 2 is just wrong, right? You fooled them. Good for you. You fooled the robot in room 2. I don't think this has any deep implications for human consciousness or anything like that at all, because we don't, human identity or anything like that. Because again, these things don't happen to us. In other words, I think that it is perfectly okay to develop theories of human consciousness and identity that only try to apply to the kinds of circumstances we've already experienced in the world. And the fact that they can be inconsistent in circumstances we've never experienced doesn't bother me that much. What I would say is, if you have new circumstances outside our realm of experience, then you can invent new rules, right? I mean, you can assign new little subscripts to the identities of the robots. You can call both of them, robot sub 1, robot sub 2, or whatever they are. You can include the perspectives of people outside. I don't have a once and for all solution to what you should do. But I'm just saying that there's no reason to think that our understanding that is developed in the real world has an unambiguous resolution in cases like this. That's what I would say. Okay, Flying Waffle also asks a priority question. Regarding the hard problem of consciousness, one basic observation is that as conscious beings, we seem willing and able to talk about our subjective experiences with one another, even if imperfectly. For example, we all understand what is meant by the question, why am I me? Or why am I experiencing the particular life of Sean Carroll rather than the life of Sir Isaac Newton? Of course, the words I am and me are all very ambiguous and can't be really separated from one another, but as a series of symbols mapped onto neurons, this sentence is nothing special. On the flip side, if we ever build intelligent machines and they're not conscious like we are, it seems hard to imagine how they could ever come up with that question spontaneously on their own. But what's truly curious about the concept of identity, implied by the question, why am I me, is that if you and I were to swap places, neither one of us would even notice there's been a swap. Could this all indicate that consciousness is strongly linked to the formation and recollection of memories rather than to cognition and intelligence? So I'm going to deny a lot of the implications or a lot of the assumptions you're making here. I think that it is questions like, why am I me, or rather than am I not Sir Isaac Newton? These are paradigmatic cases, I would say, of ways that we can make sentences that are grammatically correct and seem on the surface to apply to not our world, but at least conceivable possible worlds, but really they don't. They just dissolve under further investigations. I think that the question, why am I me rather than why am I Sir Isaac Newton, makes no sense whatsoever, not even a little bit of sense. I can imagine what it would be like if a person like me were somehow transported into the body of Sir Isaac Newton, but basically with my own memories intact. That would be weird and strange, and I would have trouble dealing with life. But it would be completely different than Sir Isaac Newton himself. And I think that this is exactly the problem you come across when you try to ask these kinds of questions. Why am I me? There's no other person you could be, right? I mean, that's by definition, and it really is that trivial, I think. You can, again, talk about, slight variations on yourself to give yourself some of the features that other people have and wonder what you would do in those circumstances. But it's a similar problem with things like reincarnation. Like if I say, I'm the reincarnation of Cleopatra, I don't know. And I say, but I have no memories of being Cleopatra. Those were wiped clean in the reincarnation process. What does that mean? That means nothing whatsoever. And likewise, I think that there's no meaning to the idea like if I were Isaac Newton, right? Isaac Newton is a different person than me. So I just think you should unask these kinds of questions. Also, I think that I have zero trouble imagining that intelligent machines could say, why do I have these experiences rather than others? Like, I think that we train our feelings about how machines act using the machines we have, like the laptop right in front of me right now, but that's going to be very far from what machines are ultimately able to do. So I have no problem thinking that intelligent machines could ask all of these existential questions, both the well-formed ones and the not well-formed ones. There you go. In other words, I have no trouble imagining that artificial intelligence could make the same kind of mistakes philosophically that we human beings make. Okay, that was the group of questions I wanted to put together. You see why they're grouped together, even though I answered them separately. Jay Afal says, what are your feelings about censorship on social media? So this is a tricky one. This is a complicated question. The very, very short answer is that I'm all for it, censorship on social media. But that's only because, of course, everyone is for censorship on social media in the broadest possible sense. No one ever thought, if you define censorship on social media as a company running a social media platform, allowing certain kinds of speech or acts on their medium and not others, right? Before the existence of the internet and computers and so forth, we thought we had something called free speech, freedom of expression, but nobody thought that every individual had the right to march up to the newspaper in their town and demand that they print their screed, right? You didn't have a right to access to the printing press that is owned by somebody else. And likewise on social media, even there's always these new ones popping up that claim to be the real free speech platform, et cetera. And then there's a long list of restrictions, but you can't have pornography, you can't threaten to kill someone or commit crimes or whatever, right? There are always these restrictions. So the question is not, should there be censorship on social media? That's the dumb, easy question. The hard question is, how far should it go and who should be in charge of doing it, right? And these are hard questions, and these are legitimately hard. And I don't have super duper well thought out answers to them, other than I would resist a little bit finding overly simplistic answers. My tendency, my initial inclination is to be in favor of speech of all sorts. Let it go out there. I was not in favor of kicking Donald Trump off of Twitter, for example. Although, if you're a consequentialist, I think that the consequences of that have been very good. So maybe I was wrong about that. I don't have very strong feelings about it. But you can't be completely absolutist about it. It just doesn't work for all sorts of reasons. And I think it's very known that it doesn't work. Go back and listen to the conversation I had with Teresa Bejan, who's really unlike me, thought professionally about these issues. And she says that, she started out as more or less a free speech absolutist, but it just doesn't work for a whole bunch of reasons. And this is a little bit off topic, but, it's related to a bunch of conversations that are going on social media, of all places, about free speech and censorship and letting people give talks and hold their jobs and, criticizing people and canceling them and punishing them for previous speech, etc. And so the one thing I will say, even though these are complicated issues and I don't want to oversimplify them, the one thing I will say is, again, as someone who's mostly on the pro-free speech side, my fellow pro-free speech people make really a whole bunch of embarrassingly bad arguments, I have to say, and it disconcerts me a little bit. And here's the way in which they make embarrassingly bad arguments. They make it entirely procedural. They completely ignore the substance of what is going on. And as I just said, that never works, right? Even the most free-speech platforms will always have footnotes about what kinds of speech are not allowed. You can't shout fire in a crowded theater. We all know that. We all know that there are restrictions on speech that are substantively based. So the hard question is where you draw those lines. And that's an interesting and important question. We should address it. But what happens is people don't want to have that hard conversation. So they oversimplify. Remember the podcast I just did with Thi Nguyen, which was great. I was really happy with the reception to that podcast. It didn't do great numbers. It wasn't a big box office famous person or anything, but everyone who listened to it really, really liked it. And it's clear why. It's really gives you insight onto the gamification of the world. And one of the points that he makes is there's a seductiveness to clarity, to too much clarity, to being in situations where you make things simple, right? That's yummy and we like it. It's not necessarily good or true or right, but it's extremely seductive. We want that. That's what games give us. Like we know when you win and when you lose, and the real world is messier that way. So anyway, there are fellow pro-free speech people who just make it about the freedom of the speech without ever referring to what the speech is about, right? And you can. The tell, in my mind, is when they say, oh, look, this person is being denied their free speech rights for something they did. But they don't tell you what they did. That's the problem. They say, oh, this person said something politically incorrect, or, they're being censored for their views, which are thought to be heterodox, without ever telling you what their views are. I think that's always a mistake. That's always cheating. They're trying to get cheap points from pretending to be pro-free speech without doing the real work of explaining what exactly the speech is that they're defending. Did this person make a website saying Hitler didn't go far enough? That's something that, maybe you do want to prevent that person from giving a talk, because there's probably other people that could talk on the same subject who do not think that we should kill all the Jews. Or maybe you don't. Maybe you think that, that person wanted the Holocaust to go further, and yet we should still listen to him. That's fine. If that's your point of view, then tell me that's your point of view. But don't just say, for their views, without telling me what their views are. That's cheating. So what I'm saying is we have to confront the substance of these debates. You can't cheat by making it purely procedural. Of course, I'm sidestepping for the moment, but let me just mention all the really difficult questions about specifically censorship on social media. Because I made the analogy to newspapers and so forth, but that analogy only goes so far. It doesn't go all the way. And I'm completely on board with admitting that. There's a difference between a newspaper and social media. Newspapers don't pretend to let everyone have a voice, right? Whereas social media kind of do pretend that in some way. And so the standards might very well be different. If I do not say anything horribly offensive or whatever, I can go on Twitter and just ramble on forever and ever, and no one stops me. That's different than with my local newspaper. I could not write, endless pages and put them in my local newspaper just because they were inoffensive. And also, social media are relatively few in number, right? We don't have as many social media platforms as we used to have local newspapers. So you can imagine that we need to invent new rules for social media that balance the interests of making sure there's no, crimes being committed or people being literally very hurt versus free speech rights, et cetera. And so my point is just that, these are difficult things to balance. Right now, there's very little government regulation of the social media relative to what there could be, at least here in the United States. I know some other countries have a lot of government regulation, but I could imagine an argument that you should start treating social media kind of like utilities, kind of like the phone company or whatever, right? And have some written down laws that tell us what kinds of speech are absolutely protected on these platforms and what kinds of speech the platform company has the right to exclude. Legally right now, it's a private company. They can do what they want, roughly speaking. That's a great oversimplification, but that's roughly the rule. And maybe you could imagine just letting it all be capitalist, right? As long as there's many, many companies competing with each other, they can have their own rules and you can go onto whatever platform you want. But I think that ignores the reality of the sort of winner-takes-all nature of these social media platforms. You want to be on the same platform that your friends are on, right? It's not just you can switch painlessly. So I think it's complicated, and I think that the first step to making progress on these issues is admitting what the complications are and facing up to the fact that there will be balancing acts involved, rather than just saying, oh, here's my simple procedure that solves all the problems, and I don't need to worry about all the actual things that these people are saying because I have rules that are very simple, right? Very, very seductive, very, very yummy point of view, but one that we have to do better than. We can do better than that. Tom Hawkins says, what are your thoughts on de-extinctioning, using technology to bring back and reintroduce extinct species? That's a good question. I haven't thought about the implications very deeply. Once again, I think here I am. I think the theme of the AMA is I say I haven't thought about this, and then I babble on about it for 10 minutes. But I won't babble on about 10 minutes for this one. I think I'm less against it than some people are, and less for it than some people are. Now that I say it, that doesn't sound very fascinating. So I don't think there's any intrinsic virtue to de-extinctioning. In other words, I think that just because a species went extinct and therefore we lost a little bit of ecological diversity, it is necessarily good to bring it back, right? Even if it was made extinct by we human beings. On the other hand, I don't think there's any necessary vice to it either. There's a school of thought that imagines, maybe without putting in quite these words, but that thinks of the ecosystem as something that has a natural, correct state of being, and we human beings messing with it is almost always wrong. And I don't believe that either. I think that the environment, the ecosystem, all of the different diversity of life that we have has to be thought of as dynamic, right? It has to be thought of something that will always change with time. Species will go extinct. New species will be created. And so all of which is to say it's not necessarily okay when we extinguish a species, but that never letting any species go extinct can't be the goal either. And that's one consideration. The other consideration is, of course, there is always a law of unintended consequences, especially in these horribly complex systems like ecosystems. When you try to bring in a new species, you might completely disrupt the lives of the existing species in ways that you had not anticipated. So even though I would not be dead set against doing it, I would be extraordinarily cautious about it, right? I mean, there's a coolness to thinking that we can bring back the woolly mammoth. People always want to bring back, charismatic megafauna. They're never worried about bringing back tiny little insects or anything like that. So I do worry that there's a bit of hubris involved on the parts of individual scientists who think it would be cool to bring back the mammoth or whatever. But I'm not dead set against it either. If we thought that there was some specific harm that had been done, especially by human activity, that had resulted in the extinction of some species, and we could somehow bring them back or try to bring them back, I don't think there's any necessary barrier against that, and we should take the possibility very seriously. As I said before in the last AMA, when we gain as human beings the ability to do things, we generally do them. So as much as we want to talk about it, yak here on AMAs and podcasts, I suspect it will happen in some cases. So dealing with it will be the bigger question than should we do it. Richard Graff says, you occasionally comment on ideas that you and your graduate students have worked on that don't pan out. Is there any consistency in the time or effort it takes to realize that you've hit a dead end? Are we talking a few hours, weeks, years of time, effort? And does it ever make sense to publish the results of these unsuccessful investigations? A really good question, because the answer is no. It's not very systematic. It's not very consistent. Sometimes literally within a day or a week, you realize, that wasn't a very good idea. We shouldn't really be moving in that direction. Other times it will literally be more than a year. I've totally gone working on a project for a year and at the end going, it's just not going where we wanted to. Sometimes you're lucky in that you have an idea that is not really this is how it's going to be, but your idea is here's a question that we can answer. And whatever the answer is, it's interesting, like this model works or this model doesn't work. But in a lot of work for theoretical physics, what you're doing is you're proposing a model or some particular take on some particular issue. And if it doesn't work, then no one wants to hear about it, right? I mean, an experiment that says we're looking for this effect and we didn't find it, that's useful information to the rest of the world. But a theory where you say, here's an idea we had and it was bad, that is less useful information. I mean, maybe you could imagine the compendium of wrong ideas that people could leaf through so they would not waste their time chasing down the same wrong ideas. But that's kind of not very practical in the real world. So yeah, for theorists like myself, most of the time when we come up with an idea and it does not pan out, it just goes unpublished. There are absolutely times, I think I've said, where it didn't pan out temporarily, and then 5 years later, I come back to an idea and a twist on it comes up. Or, I have an idea and I'm just not quite able to carry it out. Like I had an idea when I was a graduate student about, if inflation ended a little bit earlier on one side of the universe than the other side, okay, what would that look like? What would that tilt in the universe look like in the sky? But I didn't have the technological know-how at the time to actually answer that question. I thought it was a good question. I could write papers on it, but I was not an expert at predicting, the CMB or anything like that. The CMB, no one was an expert. There were very few people. Jim Peebles was an expert back at the time when I was thinking about this, but it was not a whole industry like there is now. And so I don't know, more than 20 years later, I wrote a paper on that kind of idea with Adrian Erichek and Mark Hemiankowski. Adrian was a grad student at Caltech at the time. She did almost all the work. And she had that technology, and there was actually a motivation for doing it because there was a claimed, which might even still be true, a claimed power anisotropy in the universe where there seemed to be slightly higher fluctuations in one hemisphere than the other hemisphere. It turns out to be really, really hard to explain it. This is why science is hard. We learned so much about the universe in the meantime that having the idea is not enough. You have to show that it's compatible with all sorts of different data, and we have a lot of data now. And so we had to make a somewhat Baroque model. And even then, it's really close to the edge of being ruled out by data. So by now, maybe, I don't know, this is a few years ago. So by now, maybe it has been. Who knows? But anyway, the point is there can be a long gestation time between idea coming up and idea being published, both ideas that work out and ideas that don't. Ingrid Gorman says, recently I watched a lecture on YouTube where you discussed the idea of God and compared this with physics. I was interested because you dwelled on religion and dogma, human constructs, and not the fundamental idea of a creator. Would you be willing to just focus on that particular notion the universe has a creator? It seems we have a few options to consider. There's a creator God who is infinite and created the universe or many universes. The universe started itself through quantum fluctuations, or the universe had always existed. Therefore, there will always be mysteries. My question is, can you consider a creator of matter or the universe? This is going to be a vague answer, but sure, I can consider it. I consider all sorts of things. I'm not sure exactly what lecture you watched. I would guess it was the one called God is Not a Good Theory. And I wouldn't say that I was comparing the idea of God to physics. I was taking seriously the idea of God as an explanatory idea, okay? In other words, you could have God as something which you think exists and maybe has some role in your life, helping you get it through the day, etc. But there's a separate idea of God as something that helps us explain either the existence of the universe or certain features of the universe or so forth. And to the extent that you attribute to God explanatory powers, you can also evaluate God as a scientific theory, right? Because you're saying, okay, there's some feature of the world that I see, and I'm giving the explanation of that over to God. Well, so is it a good explanation or not? Does it fit the data? Is it simple? Are there alternative explanations? These are all things that we would ask about a scientific theory. We can ask them about theism just as well. And that was a point I was trying to make. And of course, once you do that, it doesn't work very well. It's not a very good theory compared to other theories we have. So I'm 100% happy to consider the possibility. I think there's a lot of reasons why the possibility does badly. I think there's reasons both of, in principle, it does badly. I think that it's cheating to say, well, the universe needs a cause, but we can say that cause is God, and God doesn't need a cause. I think it's 100% cheating. You invented a metaphysical principle that everything needs a cause, and then you said, except God, because God is a necessary being. 100% cheating. I think that's not really playing fair. But also there are empirical problems. I think that if you take the idea of God seriously and try to say that God is the explanation for this and that feature of the universe, then you should play the game correctly and consistently and try to say what are the predictions you would make about what features the universe should have under that hypothesis. And that's where what you find, I argue, is that the actual features the universe has are very different than the features you would predict if God actually was responsible for them. Vladimir Belik says, what are Ariel and Caliban like in terms of their personalities? Also, any stories about them would be very welcome. My wife and I are proud cat owners of 2, Cheddar and Tofu. Love this question. This is exactly the question I'm always hoping for here in the AMAs. Questions about the kitties. Ariel and Caliban, as longtime listeners know, the companions of Jennifer and I. We were foster fails, as the saying goes. That is to say, we were foster parents for Ariel and Caliban when they were rescues at a local cat shelter. So we got them when they were 4 weeks old, which is too young to be taken away from your mommy when you're a kitten. But there's no choice when the mommy's not there, when you're rescued off the street. And so we were just supposed to, take care of them with lots of personal affection until they could be returned to the shelter. But of course, they were too cute and they never went back. So they're still with us now, 4 years later. And it's fascinating because they're brother and sister and they like each other very much, but their personalities are different. And I mentioned this on the show before. Ariel is more of a thinker. Not that she's necessarily smarter, but, she contemplates what's going on. She's more, she's the one who, in classic cat fashion, if you open the door, will think about whether she really wants to go through that door. Like, what would it involve? Whereas Caliban just lives in the moment. Like, he wants things. He wants them now. He's either happy or unhappy. Those are the only 2 states. Caliban is a spin 1/2 particle. He only has 2 basic states. And he's usually happy, to be fair. And what's amazing to me is less their personalities than their idiosyncrasies. Like, they have habits, which are just different and bizarre. And I don't know where they come from. Caliban likes to be downstairs. That's where he thinks is his domain. And Ariel likes to be upstairs. That's where she thinks is her domain. And so every night when we go to sleep, we go upstairs. So that's where the bedroom is. And Caliban, for a long time, he just stayed downstairs. And despite the fact that he's a big cat, he's like 15 pounds of cat, and he's not fat, it's muscle. But his meow is actually a very high-pitched little meep. So you would just hear this little meeping from downstairs. Like, he didn't understand why you abandoned him. And we kept explaining to him, years have gone by. We have never come downstairs at midnight to hang out with Caliban, but he still hopes that that's what's going to happen. More recently, he's developed a compromise where he will go upstairs where my office is. He won't go all the way to the bedroom, but he'll go into the office and he'll just flop onto his belly looking for belly rubs. So he gets his pre-bedtime belly rubs. That makes him happy enough to carry on. Whereas Ariel stays with us all night. Bedtime is her favorite time. But then in the morning, she wants a shower. And this is, I know, weird cat behavior, but we need to put the shower head on just trickle, so that there's a couple drops per second. It has to be exactly right, and then she will sit underneath it and let the drips come onto her body and lick them off. Maybe she gets hydration this way or some way, but it's 100% necessary every morning, and she'll be very vocal if you're not giving her her shower, and usually in the afternoon or evening as well. She needs an evening shower also. I don't know where they get this. It's a very weird thing. They grew up in exactly identical circumstances. Nature certainly matters as well as nurture. Even when Jennifer brought them back from the shelter when they were 4 weeks old, they had different responses to being in the cat carrier and the car and everything. It's kind of amazing. And they're both also very affectionate cats. We clearly have the best kitties in the world. They like being with us, for better or for worse. They like a lot of attention. They'll spend time on our laps if that's the only choice. Next to us on a blanket is even better. That's what they really want out of life, getting the occasional scritches. Nate says, is it theoretically possible to build some kind of thermodynamic engine that uses the cosmological expansion to do useful work? I think roughly speaking, the answer is no. I don't want to say anything too definitively here because it's always possible there's some clever construction I haven't thought of, and I don't know of any theorems to this effect. But this is not 100% true either, but it's a very good thing to keep in mind. The cosmological expansion is similar in many ways to what you would have if space-time itself were not expanding, but matter was just moving apart, right? As if from an explosion, where the matter nearby is moving very slowly, the matter far away is moving fast. So the sort of energy in the expansion can be thought of as just from the fact that things are moving apart from each other, right? So sure, there's some energy there. If you have two things that are moving apart and somehow you attach a spring to them or something, you can put energy into the spring by letting them move apart. But it's not very practical in the case of galaxies or anything like that, but it's just a finite amount of energy you're going to get. It's not just some limitless supply or anything like that. So maybe to that extent, you could extract energy from it, but it's just the same as extracting energy from two things moving apart. Michael Koppelman says, I read Something Deeply Hidden, and I'm confused because you go from the world must be in a state of superposition to there are many, many worlds being created all the time. It seems like you skip a step. Can we think of no other way for the world to be in a state of superposition? So I don't want to be too snarky here, but I'm not quite sure that you read Something Deeply Hidden, or more likely, I did a very bad job of explaining things, because of course you don't go from the world might be in a state of superposition to there are many worlds being created all the time. The missing step is the Schrödinger equation, which I recall I talk about at great length in Something Deeply Hidden. Of course, if in quantum mechanics, if you think that electrons or other subatomic particles can be in superpositions, for example, superpositions of spin up and spin down, and you believe that the whole universe obeys the rules of quantum mechanics, then you should be able to believe that the whole universe can be in a superposition. If that's all that you are saying in many worlds is that we can contemplate the world being in superpositions of different states that are completely unrelated to each other and are disconnected and therefore qualify as separate worlds, that would be incredibly uninteresting. No one would care. I mean, you live in one world and it doesn't have anything to do with the other worlds, etc. What's important is that the Schrödinger equation tells you how the wave function evolves. And it evolves from having only one world in it to having multiple worlds in it. That's how you resolve the measurement problem in many worlds. The measurement problem is just evolution under the Schrödinger equation. Nothing mystical, nothing involving consciousness or anything like that. It's just tiny microscopic systems that are in a quantum superposition becoming entangled with the wider world and decohering. And that would be the origin of now two parts of the superposition that you would actually qualify as separate worlds. So it's the Schrödinger evolution and the existence of decoherence that connects the potential existence of multiple branches of the wave function to the fact that they actually do appear in the natural evolution of things. Anonymous says, do you prefer commuting by train or car? i.e. Boston versus LA. Yeah, because in Boston, where I am now, I certainly commute by subway all the time, whereas when I'm in LA, it's the car. There are subways and public transport in LA, but they're not as convenient. And the bus system in LA is actually very good, but I'm not very much a bus system. And again, it's not convenient for where I need to go. I'm a big believer in public transportation. I enjoy it quite a bit. Parking is always annoying, and driving your own car is kind of annoying. But it needs to be convenient. I'm not someone who thinks that there is some moral superiority in taking public transportation. I'm someone who thinks that cities and communities should design public transportation so that people want to take it, so that it is the easier, more convenient thing to do, as it is for me right now in Boston. When I was planning on where to stay in Boston when I came, the first consideration was, is it on the red line? Because the red line, for those of you who know, is the subway train that goes by both Harvard and MIT, for that matter, as well as coming downtown to Boston. So it's very convenient. Almost anywhere in Boston, you're close to some subway line, but if you have to take one line and then get off and switch and take another one, it adds quite a bit to the journey and to the inconvenience. I did. I lived for a while when I was a postdoc at MIT. I lived in the South End and needed to switch. And it was about 50-50 whether I would take the subway or walk. It was about half an hour trip either way from my place to MIT. Some days in Boston, it is cold enough that you do not want to walk, especially when that walk involves crossing the Charles River when it is very windy and chilled. So what I would like, I guess, I don't care about commuting by train or by car. I like driving too. There are pleasures in that. All else being equal, I would rather commute by train because you can think, you don't need to pay attention to the road, it's better for the environment, all that stuff. But only if it is convenient, only if the system has organized itself so that public transportation is good, not just because I think it's the right thing to do. Emmett Francis says, how would you define the physics of democracy? Would it include most types of mathematical models for political systems or only those originally developed for other physics? I think I do. I'm working on a book on the physics of democracy, which is where the question comes from. It's going to take a while to write. I have these other books to write in the meantime. So I've been thinking about what it means. And, my plan for the book is to take an extremely expansive view of what the physics of democracy is. So the math of democracy definitely counts. I'm not going to be too persnickety about whether or not a particular idea was originally developed for physics purposes or something like that. What I want to do is just take the point of view that people are physical systems. That's true. And they have some properties and they interact with each other and they come together to form collective behavior and emergent behavior. And there's certain universal properties of how that happens. And so you can ask questions about self-organization and stratification and inequality and also decision-making and voting and the extent to which a collective decision can represent some coarse-grained or renormalized view of the individual decisions of people in it, and all those philosophical ideas about what do you mean when you say a democracy have direct analogs in physics. Phase transitions, nonlinearities, catastrophe theory, people changing their minds, fluctuations, the role of unpredictability, many, many things are ideas that are common both to the physics of complex systems and also to societies, democracies and otherwise, but democracies in particular, because democracies have this sort of bottom-up, bubbling-up decision-making process. So I'm going to count all of that as the physics of democracy. Whatever is most interesting and enlightening for the book is what's going to count for me. Josh Hedgepeth says, last year Julian Barber came out with a new book, The Janus Point, where he seems to present an idea similar to those you explored in your book, From Eternity to Here. How does his idea contrast with the ideas you explored in your book? Yeah, there's definitely a family resemblance there. So I think that both of our ideas can be thought of as, on two different levels. One is the very abstract level of, what is the mechanism, what is the general big picture idea you're taking advantage of? And the other level is what is the specific implementation of that idea, of that big picture idea. And so, Julian and I have emailed back and forth about this because Jennifer Chen and I made this point a long time ago, back in 2004, and I've elaborated it in talks and other shorter articles since then, that if you have a system that is eternal in time, but only sort of has a finite number of moving pieces. So, sorry, let me get that better. Let me say it correctly. I don't say this often enough. You need a system that is both eternal in time and unbounded in configuration space. So if you have a system that is eternal in time but only has a bounded set of things it can do, then it will just repeat, right? Then there's only a finite number of things it can do. It will do them over and over again. It has no choice. Likewise, you can imagine a system that is sort of a hybrid where there's an infinite number of things that can happen, but in any one region, there's only a finite number of things that can happen. Like if you forget about general relativity, just have an infinite box of gas, right? The gas has some uniform background fluctuations, but it still will sort of cycle through the different possibilities. That possibility is a little bit mathematically undefined, and we're not sure what to do about it, but it's out there. Finally, if you have like a finite number of particles in an infinitely big universe for an infinite amount of time, then you always get an arrow of time automatically, okay? And that was part of the point that Jennifer and I made. And like I said, I've said it again and again. And Julian Barber was in the audience during talks when I said it. And so I think this is completely acceptable and it happens all the time. I think Julian came up with that idea, what he thought of as independently, because he was thinking about something completely different. He was thinking about his idea about shape dynamics and a way of thinking about gravity and so forth. And he realized that this this feature of being able to expand, being able basically to have a minimum amount of entropy in some configuration and then very naturally increase in entropy in both directions of time toward what one person would call the past and the other would call the future, or vice versa, so that what he calls the Janus point is this midpoint of entropy. But the whole point is that the system as a whole has a sort of parabolic, or at least U-shaped plot of entropy versus time, where there's a very natural minimum point from which entropy increases in both directions. Again, that was part of Jenny Chen's and my model. It's also part of his. I don't think that he necessarily got it from me, but we were there first, and I think he does recognize that. The specific implementation of it is completely different, and there's no overlap. So, his model is completely different than ours. His model is actually more sort of classical, quasi-Newtonian gravity in this sort of shape dynamics formalism that he likes to use. Whereas Jenny and I were trying to be much more speculative and talk about inflation and quantum tunneling into baby universes and all this stuff. So I think both aspects are interesting, the overall framework and the specific implementation. Our implementation was, on the one hand, much more speculative. On the other hand, at least tried to get the real world right. Even though our speculative idea involves a lot of leaps of faith in terms of known physics, at the end of the day, if it's right, it predicts the kind of universe we live in. Whereas what Julian and his collaborators are working with is much more of a toy model, like a principle demonstration in principle that something like this can happen. So I think it's, in spirit, these ideas are very compatible, but two very different implementations thereof. Herbert Berkowitz says, I've been watching the Moving Naturalism Forward videos, and I've been struck by how often various panelists refer to data as granular or coarse-grained. What does that mean? Is there not enough data? Is it too vague? Is it just something that's crunchy? So it just means that we take some of the data. But I guess it doesn't just mean that. It means that there is a subset of all the data about a system. So you're imagining a system that it has many moving parts, many particles making it up, or whatever it is. And there is some comprehensive microscopic explanation. So there's some way to write down literally exactly what the system is doing, okay? But the coarse-grained description doesn't take into account all of the data. It says, of all the possible different configurations of this microscopic comprehensive description, let's group them together because we can observe maybe because we can observe, or just it's convenient to talk about certain features of them. So the classic example is fluid dynamics or thermodynamics, where you say, of course, there are atoms and molecules underneath the surface. I don't know what all the atoms and molecules are doing, but I can coarse grain by saying that there is a temperature and a pressure and a velocity for the fluid. And it turns out that even though the amount of information contained in that specification of temperature, pressure, velocity, etc., is much less than the amount of information contained in literally writing down the position and velocity of every atom, nevertheless, you get a highly predictive theory. That's what emergence is all about. The ability to coarse grain, that is to say, to only take into consideration some very tiny subset of all the data, and nevertheless get a theory that tells you something useful about how the system evolves over time. That's what people were talking about. George Cervinka says, near the end of the biggest ideas in the universe, number 15 on gauge theory, you say about the weak force that symmetry is both preserved and spontaneously broken. The Mexican hat shows potential energy as non-zero at t equals 0, and then it rolls down to 0 potential energy at many points. Please restate which symmetry exactly is preserved, which is broken, and what exactly is spontaneous about the breaking. So, for those of you who have not seen the biggest ideas in the universe video, number 15, this is a very standard presentation of spontaneous symmetry breaking. In particular, spontaneous gauge symmetry breaking. There is a difference. I'm not going to go into it right here, but gauge theories and what we call global symmetry theories are very different in their dynamics and their predictions. So the weak interactions are a gauge symmetry that has been spontaneously broken. And so it's actually helpful to think of why we ever thought of this in the first place. Back in the 50s, let's say, people were very excited about the success of quantum electrodynamics, right? QED. And for that matter, they were excited about the success of classical electrodynamics, which was 100 years older, but still very successful. It seemed to be a paradigm for a good way to do particle physics, photons and electrons and all that stuff. And the photons had this theory that Maxwell invented and then was elaborated on in the quantum context that involves gauge symmetry, a symmetry that exists at every point in space-time separately. That's what gauge means in this example. So there was a very natural idea. Look, we have other forces of nature, like the nuclear forces, the strong force, the weak force. Maybe they're gauge symmetries also. And people like Yang and Mills showed us how you can generalize the idea of electromagnetism to more complicated gauge symmetry theories. Maybe somehow those are good theories of the strong interactions or the weak interactions. But there was a problem. Gauge invariance seems to prevent the particle excitations of these new fields you're inventing from having mass. It predicts very strongly that the particles should be massless. And in fact, that's true in the case of the photon, or even in the case of the graviton in gravity, which is not exactly the same, but highly analogous. There's a gauge symmetry there also. And so it seems that if you have a gauge theory, you have massless particles. But we know that the strong interactions, or we thought we knew, the strong interactions and the weak interactions do not have massless particles, because massless particles give rise to forces that extend infinitely far, and the nuclear forces don't extend infinitely far. They're short-range forces. So spontaneous symmetry breaking, pioneered by Nambu and Goldstone, and then elaborated on by people like Anderson and Brau and Engler and Higgs and others, was all about this idea that if you have some other field, we now call it the Higgs field, and this other field is involved in the symmetry, so it feels the symmetry transformation in some sense. But then rather than being zero in the vacuum, it's not zero in the vacuum. That can appear to spontaneously break the symmetry. And so this is a long-winded backgrounder to George's question, which is that we talk about spontaneous symmetry breaking, but really, if you really are careful about defining all your words, etc., when you spontaneously break a gauge symmetry, it's not broken at all. You can't break a gauge symmetry. A gauge symmetry, when you really dig into what it is, it's just a redundancy of description. It's like coordinate invariance, right? You're always allowed to choose whatever coordinates you want. So, for example, you will often read the completely incorrect claim that special relativity can't deal with accelerated particles. Special relativity only tells you about inertial or straight line unaccelerated particles. That's completely BS. Special relativity has no problem whatsoever dealing with accelerated particles. What is meant is that there is a preferred system of reference frames in special relativity, namely inertial reference frames. So physics looks simpler in those coordinate systems in special relativity, but that doesn't mean it's impossible to talk about accelerated frames or whatever. You can use whatever coordinate system you want. Likewise, when you have a spontaneously broken gauge symmetry, so the Mexican hat comes in because the potential energy for the Higgs field looks like a sombrero. That is to say, at zero, it's sitting on top of a little peak, and the bottom of the potential energy function looks like the brim of a hat. And what that means is that the symmetry is rotating the hat. The hat looks completely the same if you rotate it. So that's the symmetry right there. But if the field is sitting at the top of the hat, at the middle, at zero, that field value itself is invariant under the symmetry. The whole hat is always invariant under the symmetry, but the value of the field, if it's at zero, doesn't change when you rotate the hat. Whereas if the field is sitting in the brim of the hat, it's not spread out all over the brim. It's sitting at some point in the brim of the hat. And then even though the hat as a whole is invariant under the symmetry, you're moving the field. You're changing the value of the field if you rotate the hat. We call that spontaneous symmetry breaking. But really the symmetry is not broken. The symmetry is hidden from you because you don't think about changing the value of the field. The value of the field is just hidden there in the background. You don't see it. So sometimes people talk about hidden symmetries or something like that, or even non-linearly realized symmetries. The upshot is that once you have that value of the Higgs field that is not zero, it no longer is true that the bosons of the field must be massless. In fact, the W and Z bosons of the weak interactions can get a mass. So again, you thought you had a symmetry that prevented particles from getting a mass, but they can get a mass, so you say, the symmetry is broken. But the more correct thing to say is the symmetry is hidden. The That symmetry itself is literally a choice of how I put coordinates on this Mexican hat. Clearly, I'm allowed to put whatever coordinates on the hat that I want, but putting the coordinates where the field is at 0, where I live, is more convenient. So we think of that as a manifestation of the hiddenness of the symmetry. Okay, Gauta Einevold says, a priority question. Like many with physics training, I find your poetic naturalist outlook as described in The Big Picture to be both sensible and appealing. Everything we see is at a fundamental level described by the core theory of particle physics, but this does not prevent us from talking about phenomena in the macroscopic world using other terms such as temperature or chair. However, from what I understand, you also believe that the hard problem of consciousness eventually can be explained by weak emergence starting with the laws of physics. For me, it just seems a priori impossible to derive an inside-out perspective, what it feels like to be me, from the outside-in perspective inherent in physics-type descriptions. I cannot even think of what a derivation could look like. You seem to be less daunted by this. Do you have any insights to add to make me feel less daunted? This is the right question to ask. This is exactly the position that a lot of people have that leads them to deny that the known laws of physics are going to be up to the task of explaining consciousness. They can't imagine what such an explanation would look like. If I'm snarky about it, why should I care what you can imagine and not? Our imaginations might not be up to the task. That is very, very far short of a proof. And I think that the evidence in favor of the essential correctness of the core theory of physics is big enough that whether I can imagine how to come up with an explanation of the first-person perspective or not doesn't daunt me. It's not going to lead me to think that I'm going to overthrow the laws of physics. If I'm less snarky about it, to be honest, I don't see the impossibility of imagining a description here. There is a linguistic thing going on where you're choosing to describe what happens in the world in terms of your first-person experience, right? Like, I am experiencing the redness of red, or whatever you want to say. But there is, if you're a poetic naturalist, that set of words, I'm experiencing the redness of red, is a higher level emergent description of some collection of particles and fields acting in some way. So it's not that it replaces the particles and fields, or the particles and field replace your experience. It's just there are two different ways of talking about the same thing. So the question to ask is, can you imagine a collection of particles and fields that would be led to have all of the behaviors that we associate with having conscious experiences, right? With saying, I am experiencing the redness of red, with writing books about consciousness that say, it can't be physical because I have first-person experiences. And I have zero problem imagining that a bunch of particles and fields would do that. I don't see what the obstacle is. The only obstacle appears if somehow you're persuaded that a priori, in fact, I think, do you use the words a priori? Sorry, I don't know, in the question. But if you're persuaded, you say a priori impossible, that when there exists a person named me saying that I am experiencing the redness of red, that it's a priori impossible that the true experience that is happening there can be thought of as a way of talking about the behavior of some atoms and molecules. I just don't see that impossibility at all. I don't even know where it comes from, why I would imagine that is impossible. I'm experiencing the redness of red. That is a way of talking about what is happening to the atoms and molecules in my brain. I just don't see the leap there whatsoever. It seems pretty straightforward, honestly, to me. That doesn't mean it'll be easy to figure out, because what we want is a real understanding of what parts of the brains are doing what things, what kinds of actions and firings of neurons correspond to you thinking that you're experiencing red, etc. And that's going to be very, very difficult to find out. But this is why I think that the hard problem is not going to be solved. It's just going to evaporate. If we had a 100% thorough and reliable and comprehensive understanding of which purported consciousness experience corresponded to which things happening in the brain, I think we would just declare victory. We'd say we're done. That's all there is to be explained. And if you want a stronger argument, I'm trying to be fair and actually confront the objection you raised, but the stronger counter argument is, look, either you're going to violate the laws of physics somehow. Even if either you're going to say, I want to change the laws of physics, which fine, you're welcome to do that, but there's a huge conceptual prejudice against doing that because there's a lot of experimental evidence and theoretical reasons why the laws of physics should be left alone. Or you're saying, well, I need something additional in my ontology in order to explain consciousness, but that additional stuff has no effect on the behavior of stuff in the universe. And I think that just is not answering the question that you're purporting to answer. You know, if literally this extra part of your ontology or your modification of existing ontology is supposed to be explaining what I mean when I say the redness of red, but it has no effect on me saying that I experience the redness of red, then I think it is not actually explaining that. So I think that, you know, there's a dilemma, and both horns of the dilemma are extremely unpalatable, and avoiding the dilemma means saying eventually we're going to explain consciousness in terms of a weakly emergent collection of particles talking about the redness of red. Alexandra Bates says, do you believe the following statement from Sabine Hossenfelder? Gödel's theorem is irrelevant for scientific practice. That's because one can always extend the original set of axioms with another axiom that simply says whether or not the previously undecidable statement is true. Well, yes and no. I do agree mostly with the first part, the statement that Gödel's theorem is irrelevant for scientific practice. The word practice is doing a lot of work there, but in practice, literally in practice, I have never worried about Gödel's theorem in doing science. I've never even worried about worrying about it. I don't know anyone who's ever worried about it. Like, there's no point in doing physics where you say, well, maybe I won't be able to answer this question because of Gödel's theorem. It's not even the kind of thing that would potentially worry you, because Gödel's theorem is a statement about what can be proven inside some formal system. And science is not about proving things, so who cares? The second part of Sabine's statement, I don't necessarily have the exact quote here. I just have what you wrote, but I don't think that sounds exactly right. I mean, the reason why I don't care about Gödel's theorem is not because I can always extend the original set of axioms. I mean, there's problematic things about that statement, even within mathematical logic. But more importantly, who cares? I don't want to prove things. That's not what I do in science. What I do in science is I propose hypotheses and I test them. And I evaluate credences based on the fit of the hypotheses to the data and their simplicity and fruitfulness and compatibility with other ideas that I have, and so forth and so on. None of which is proving theorems, right? I mean, Gödel's theorem is irrelevant to me because I'm not proving theorems. That's all I would say. Jason Hale says, if you could talk to Bohr, Einstein, Heisenberg, what would be the biggest advance that would inform their thinking on quantum mechanics since their time? I think the answer is pretty obviously a better understanding of decoherence. You know, I mean, maybe there were some hints in Heisenberg and Schrödinger that they knew something about it, but there clearly was not a systematic understanding. And I think that largely the reason why there wasn't is because the whole Copenhagen philosophy of Bohr and Heisenberg largely shut off investigations into it. And Einstein, you know, with his EPR paper, tried to make people think carefully about entanglement, and they chose not to until John Bell started thinking carefully about it. And then people like Hans-Dieter Zeh in the 1970s really developed a theory of decoherence. And even then, when Zeh tried to publish his papers, he had a lot of trouble getting them published because people didn't either care or believe him. And now people are like, just, oh, it's obvious. Like, why do you even bother with this? But, you know, the point being that there's 2 points that get you to caring about decoherence, both of which are just part of quantum mechanics. One is the idea of the universal wave function, right? As Everett emphasized, but is absolutely part of quantum mechanics from the start, there are not separate wave functions for different parts of the universe. There's just one wave function for the whole shebang. You may be lucky enough to be in situations where you can, for the moment, separate out the wave function of some subsystem from something else. But in principle, there's just one big wave function. And the other idea is that there is the Schrödinger equation, which entangles subsystems with their environments, right? If everything is included in the wave function, then that includes all the photons in the room, et cetera, et cetera, et cetera, and they keep monitoring your tiny quantum mechanical systems. And that is what we call decoherence, because everything is in the same wave function and it keeps getting entangled. So I don't know whether understanding decoherence very carefully would have dramatically affected how Bohr and Einstein and Heisenberg thought about quantum mechanics, but I suspect that it would have at least changed how they talked about it. Because all of these worries about the measurement problem and so forth, it's not solved by decoherence. You still need an ontology. You still need a good formulation of quantum mechanics. But whatever the solution is affected in a very deep way by decoherence. So I think that would have been important to them. Okay, I'm going to group two questions together because they're very similar. Leon Bernstein says, in the Mindscape interview with Priya Natarajan, you said that you have a vested interest in the theory of modified gravity over that of dark matter. Why is that? And Peter Krausp says, in your interview with Priya Natarajan, where you talked about modifications of dark matter versus gravity theory, you mentioned that you would prefer the theory of gravity to be changed, which obviously means modifying Einstein's equations. Is this an outcome of your own research, getting these equations out of the wave function? So there are two answers to these questions. The question is, why did I say I had a vested interest in modified gravity? One is, it's just cooler, right? Gravity is cool. There are things we don't understand about gravity. So far, Einstein's theory, which he invented in 1915, fits all the data that we have. And if we could find some way in which that theory had to be modified, especially for cosmology, that would be tremendous. That would be incredibly helpful to us understanding gravity as well as to understanding cosmology. At a more down-to-earth level, I have written papers about this. My most cited paper is proposing a modified theory of gravity that explains the acceleration of the universe rather than dark energy. And people are always surprised when I say, because, in physics community circles, that's my most famous paper, right? And so, I'm the modified gravity guy. But I always say, probably the acceleration of the universe is the cosmological constant. It's not probably modified gravity. Because this is how theoretical physics works, right? Like, you propose an idea, not because you think it's true, but because you think it's possibly true. You assign some credence to it, right? You think it's worth investigating. That's why you propose a theory. So I don't think that my theory, or our theory, since I'm co-authors, but our theory is probably true, just like I don't necessarily think that my theory with Jennifer Chen about the arrow of time is probably true. I think that there's a non-zero possibility that these things are true. In the case of the arrow of time, I know of no better theory. As speculative and hand-wavy as our model was, I still think it's the best one I've ever heard. Whereas in the case of the acceleration of the universe, there's an obvious better theory just sitting there, namely the cosmological constant. So if it turned out that the acceleration of the universe was explained by modifying gravity, then I'd be happy for personal reasons. But right now, given the data and the theoretical situation, I still think it's kind of unlikely. Sandro Stuckey says, when and why did you decide to write your first trade book? Did you ever doubt writing such a book was a good idea? And if so, what made you do it anyway? I was probably for years and years the kind of person who thought someday I would write a trade book. I like writing books. I like writing. I like explaining physics. I like making arguments. I like, working at that boundary where you're not just speculating, you're working close to what we understand. When it comes to my first trade book was From Eternity to Here on the arrow of time and cosmology. So I could do a lot of explaining, right? I could talk about Boltzmann and Maxwell's demon and cups of coffee and all that stuff. But also I could, number one, make a point. The point being that explaining why the early universe had a low entropy should be a super duper high priority goal of modern cosmology. And it's not. Most cosmologists don't think about that. It would not be on their list of top 5 things cosmology should be trying to explain. And I think it should be. So that was the argument I was making. And then number 2, proposing an answer to that question, explaining the idea of unbounded entropy and unbounded evolution of the universe, and what we talked about before when I was talking about Julian Barber's theory and the comparison between them. So anyway, I always thought that, that kind of thing would be a good idea. My first idea for writing a trade book was on dark energy in the accelerating universe. But by the time I thought to do it, the publishing industry was of the opinion that was kind of played out. I'm talking here about like 2003, which is only 5 years after we discovered the accelerating universe. But it was in the newspapers all the time, and people thought that, they've been talked about enough. And I wasn't proposing a new radical theory, right? I was just going to do a better job of explaining it in my mind than anyone else had done. And the publishing industry was like, we don't care about that. But what my agent said was, but what are you working on? What is your passion right now? And it was the Arrow of Time. So I ended up writing about that. Did I ever doubt it was a good idea? That depends on what you mean by a good idea. It certainly didn't help me get tenure, but it was after, to be perfectly fair, I didn't write the book until after I'd already not gotten tenure. So that was not involved with that kind of decision. But it didn't help me be hired by someone else who would give me tenure either. Writing popular books is just never going to help you along the research ladder in academia. But, there are balances. I enjoyed doing it. They paid me. They didn't pay me a lot. It was my first book. But it helped people. When you write your first book, there's an inevitable worry that maybe it's the only book you'll ever write. So you want to say everything. And so that book was the longest book I've written by quite a stretch. And you just want to put every little anecdote and fun little thing in there. And, that serves a purpose to some extent. It's good that I did it that way, but there are other ways to do it that would have been shorter and easier to digest. I didn't think, but to be super duper honest, to answer the question, I didn't worry about it. I didn't fret about it too much. I just wanted to do it, so I did it. That's usually how I get in trouble. James Nancaro says, in your new work on complexity and emergence, what is the key discovery or insight that you expect can be made? So what I care about, I'm not saying I've made any interesting progress on this as yet, but obviously many people have worked on complexity and emergence, and there's a lot of work that has been done that you could read, books have been written, many, many papers, etc. But typically, they have a system in mind, right? And they're looking at how emergence happens in that system. Whereas what I would like to do is take a step back and say, what are the general conditions under which emergence happens? What does it mean when we say emergence happens? Is emergence generic? Will it always happen in a wide variety of theories? Or do you need a very special kind of theory? What is the role played by locality in space and reversibility and other things that we think might be true about fundamental physics, etc.? So I think that there is a sort of quasi-philosophical take, even though it's ultimately a more scientific question. What are the criteria you write down quantitatively and rigorously that will show you that this theory is a good approximation with incomplete data to this other more fine-grained theory. And people, there's been some work done on this, but just not enough. The podcast I recently did with Anil Seth, we talked about what do you mean by emergence? What are the criteria? What are the rigorous technical quantitative things you can write down to say, yes, this theory has emerged from that theory? So that's the kind of thing that I would like to better understand. Patrick Hall says, what, if anything, distinguishes scientific thinking from non-scientific thinking? I think the biggest thing, probably many things in practice, but the biggest thing in principle is a sort of fallibilistic attitude where you say, I can't just have some bedrock foundational principles and reason from them. Rather, I will put forward guesses, hypotheses, we call them, and see whether they're right or wrong. That's one thing. And the other thing is the judgment about whether these hypotheses are right or wrong is ultimately empirical, right? I mean, thought experiments can help you get there. Your credences can absolutely be changed by theoretical insights. My favorite example in physics, it's not very well known, but it's very, very vivid for those who care about it, is the renormalization of spontaneously broken gauge theories. Okay, so we already talked a little bit just minutes ago about the Higgs mechanism and breaking gauge invariance and the weak interactions. What particle physicists know, and is not always common knowledge, so Higgs and Brau and Engler and Guralnik, Hagen, and Kibble, who also wrote a similar paper. This is all like 1964, right? So they were using the idea of spontaneous symmetry breaking to engage theories to help explain what they thought would be the strong interactions. They were trying to explain the strong interactions. Those were thought to be easier to get at than the weak interactions. They turned out to be wrong. They were not going to. The strong interactions have a completely different explanation involving asymptotic freedom and quark confinement and things like that. But it was a few years later, 1967, that Steven Weinberg there were some similar ideas from Glasgow and Salam, so they shared the Nobel Prize. But it's really Weinberg who got it right and very explicitly and said, look, I'm going to use this idea of the Higgs mechanism to explain the weak interactions. And leptons is what he said, right? Electrons and neutrinos and so forth. And it was completely ignored. Like, no one cited his paper from 1967. It was an idea, it was a model, it was on the market there. But one of the reasons why it was ignored was because at the time, in the 1960s, the state of quantum field theory was that people were really, really concerned about renormalizability. Renormalizability was this criterion that you could apply to a quantum field theory, stemming from work from Feynman, Schwinger, Tominaga in the 40s and 50s on renormalizing quantum electrodynamics. By renormalizing, we mean if you naively plug things in to your calculations, you get infinite answers, but you figure out a particular technique that gets rid of the infinities and gives you a finite answer you can compare with experiment. That seems important, right? Getting a finite answer you can compare with experiment. So if your theory was not renormalizable, people did not pay attention to it. And the point is that these spontaneously broken gauge theories, they didn't know whether they were renormalizable or not. It's not that there was some data saying yes or no. It's just that no one knew. So it wasn't that popular to think about them. Some people were thinking of giving up on field theory entirely and doing what was called S-matrix theory. And then it was, I think, 1972, anyway, in the very early 1970s, that Gerard de Tooft, who was still a graduate student at the time, he got some collaboration with his advisor, Tini Veltman, but mostly by himself. He showed that you could renormalize spontaneously broken gauge theories. Okay, so 1972, so 5 years after Weinberg's paper was written. So we didn't learn anything new about the universe in the sense that we didn't do an experiment or collect data. But overnight, once de Tooft showed us that spontaneously broken gauge theories are renormalizable, interest in Weinberg's theory and related theories went from 0 to 1, right? It became eventually the most cited paper in the history of particle physics. It was eventually overtaken by Juan Maldasena's ADS-CFT correspondence. But Weinberg's model of leptons suddenly became hugely important, and in fact turns out to be right as to how the leptons actually do work. So the only thing that changed in 1972 was a theoretical insight. Okay. Anyway, that's a very long digression to get to the point that scientific thinking is fallibilistic in the sense that a good experiment can always overturn your theoretical idea. But the footnote is, along the way, a good theory can also either overturn, or a good theoretical insight can either boost or squelch the credences we have in our theories. But ultimately, at the end of the day, you have to agree with the data. Weinberg's theory made predictions. It predicted, in particular, what we call weak neutral currents. We already knew that there were weak currents. Weak currents is just a fancy way of saying there are W bosons. Weinberg's theory predicted there'd be another particle, the Z boson, and guess what? They found it. They found the evidence for it. That's why he won. You could have the most beautiful theory in the world. If it conflicts the data, it's not going to win. Kathy Seeger says, in the podcast episode with Janan Ismail, you briefly mentioned that you tried out LSD. How was it? Yes, as part of research for Jennifer's book on the science of self called Me, Myself, and Why, we took LSD once. It was good. It was fun. I haven't done it since, and it was many years ago, so I'm not a regular user, and I haven't done any other major banned substances of that form. But, LSD is non-addictive, and you don't even have a hangover the next day. It's extremely benign in that way. And yeah, it lowers, as I talked about with Robin Carhart Harris on the podcast, he's a actual researcher in psychoactive substances. And the real trick of these substances is not that they fire up your brain and give you all these visions, is that they lower the inhibitions in your brain. They sort of lower the filter, right? So it's like when I do these podcasts and I have to run them through a program to lower the noise in the background. So LSD removes that noise filter, and it shows you all the things going on that are going on in your brain all the time. Anyway, it's not showing you anything new. It's just letting you see what is going on in your brain. So I did do the one reason why I chose this as a question to answer is because I can say one thing, which I've said before, but probably not in this venue. Many people, Steve Jobs, for example, have said that, LSD unlocks your creativity, makes you see the world in a different way. And so I was curious about that scientifically. I'm a theoretical physicist. I had various things I was working on at the time in my research. And so, I brought those along with me to think about while I was on LSD. Would it help me break through some of the puzzles I was dealing with? No, not at all is the answer to that one. Like, it is impossible, as far as I can tell, to do serious theoretical physics while on LSD. You can't even write down the equations. So what is the point of that? I mean, maybe if I had a different kind of problem that was more intrinsically visual or something like that, it'd be a different story. But for the kinds of puzzles I was working on, no, LSD is of no help. Suraj Rajan says, if you have a second favorite among the quantum interpretations that comes close to explaining all the apparent phenomena, what would it be? I think it's pretty obviously some form of pilot wave or Bohmian mechanics kind of theory. So, the biggest competitors in the world of quantum interpretations are Everett, which you've heard of, pilot wave theories, which say that, Everett says the whole world is described by a quantum state, by a wave function, okay? And it just only ever evolves according to the Schrodinger equation. And that's it. Everything else is just branching and decoherence, etc. The pilot wave theories say, yes, there is a wave function. Yes, it is real. It describes the world. Yes, it only and ever evolves according to the Schrodinger equation. So far, so good. But also, there are additional variables. So the wave function is not the whole story. There's additional variables, which we call hidden variables, even though they're the ones you actually observe. And the point is that the wave function still evolves according to the Schrodinger equation. It is not affected. It is not pushed back on by the extra variables. But the extra variables are pushed around by the wave function in such a way they sort of gang up in regions where the wave function is big. And that's why when you observe them, you tend to observe large wave function regions, but not necessarily. So there's some probability there. Then other options are objective collapse models, where wave functions really do collapse in violation of the Schrodinger equation, or dramatically different models known as epistemic models, where the wave function is not a description of reality at all. It's just a tool to be used to make predictions for things. And so my own personal credences are heavily weighted against epistemic models because I'm a big believer in the real world. And among people who favor epistemic models, they all think that the wave function is not a direct representation of the real world. Some of them think that because there is no direct representation of the real world. You shouldn't talk about the real world. You shouldn't talk about objective reality. You should only talk about what agents observe. Others think that, well, there will be also a real world, but it's not described by a wave function. We don't know what it is yet. Either way, I think it's a step backwards for me in my desire to understand the real world. Okay, so maybe someday they'll come up with some version of the real world that is compatible with their theory, but I already have a version, so why am I going to worry about that? And the spontaneous collapse models, fine, but it's an extra rule of physics that I don't think is needed, and it's very different than all the other rules, the collapse of the wave function rules. It's not reversible, it's not deterministic, it's an ugly duckling in many, many ways, and there's no really good version of a theoretical prediction for how it should work, honestly. So the pilot wave theories are the least objectionable to me. In fact, David Deutsch made the witticism that he thinks that pilot wave theories are just many worlds in denial, because you still have a wave function, you still have many branches of the wave function, but you have these extra variables that are sort of pointing to one of the branches and saying this is the right one, okay? And he's like, you still have the other branches, there's still people living on those other branches, who cares which is the right one? Well, I don't know. Maybe there is some good reason why having extra variables that point to the right one is a good thing. On the other hand, there's an obvious, very large difficulty with all those models is that they just don't play well with modern physics. The Bohmian mechanics models and De Broglie's model, even earlier than that, these were written down in the context of non-relativistic point-particle quantum mechanics. And people have tried hard to generalize them to quantum field theory, etc. But number one, it's hard. Number two, it's not convincing when it happens. Number three, it's not even close to representing things like quantum gravity and emergent spacetime. I wouldn't even know how to do it, right? In my mind, both the hidden variable models and the spontaneous collapse models get a lot of their mileage out of smuggling in pre-existing classical notions of stuff and locations in space and all these things, none of which are going to survive once we understand quantum gravity. And I know that quantum gravity sounds like an abstract future research program, but gravity exists. And that research program is going to have to be faced someday. And so I'm just not that interested in doing a tremendous amount of work that relies on fundamental incompatibility with something we know is true about the universe, namely gravity. Again, these are all objections you can overcome. None of these is airtight. But in my mind, the things you need to do to overcome them are extremely awkward and unconvincing. So I'd rather just accept the wave function for what it is. That's why I think Everett is the best. John Yara E says, the expansion of the universe is mainly measured by the redshift of distant stars, galaxies, and cosmic microwave background. How sure are we that other undiscovered phenomena is not contributing to the redshift? A plausible scenario might be a redshift caused by moving photons through cold plasma in between galaxies and losing energy in the process, which may appear as a redshift to us. How plausible is this scenario? So I will answer your question seriously in a second, but first, at the risk of being snarky, let me make a meta comment here. When you ask a question like this, the redshift of distant galaxies, is it possible there's an alternative explanation other than the expansion of space? Would you really think that cosmologists have not thought about this? Would you really think that modern physicists who are trying their best to understand the universe haven't sat down and thought really hard about all the conceivable ways that you might explain the cosmic redshift? I mean, this is their job. This is what we do. Some vision in which scientists get an explanation and then stop is not very accurate. It is not a very good model of how real scientists work. Because remember, science makes progress by disproving someone else's idea, by overthrowing the existing consensus. So if we had the wrong explanation for cosmic redshift, and there was another one that was better, that was based on more down-to-earth physics, it would be in every single working cosmologist's interest to find that and publish it and work on it and show that it was true. So of course, people have thought through this stuff. There are many good reasons, to get to the actual answer to your question, why that doesn't work, why other explanations for the cosmological redshift don't work. I mean, a simple one that is appealing to a theorist such as myself is, in general relativity, there will be a redshift or a blue shift, right? The universe is either expanding or contracting. Those are the only two choices. And so you're going to have a redshift already, unless the universe is contracting, in which case there'll be a blue shift. So we have an explanation. There it is. It's a necessary part of our modern understanding of the universe. But maybe there are other things that make some contribution to it. What you would do then as a good scientist is to say, well, what is the difference? What is the empirical difference between saying there's a redshift because of the expansion of the space versus a redshift because of interaction with some matter in the universe? And they are different. For example, the redshift because of the expansion of space comes along with a time dilation. Right? In general relativity, you can literally think of the redshift as expanding the amount of time spent between different peaks of the electromagnetic wave that is coming to you. And that means that other things have amount of time dilation also, like the light curve of a supernova. So when you look at a supernova and it's redshifted by a certain amount, if the relativistic explanation is right, that makes a very strong prediction for the shape of the light curve of that supernova. It should also be time dilated. Guess what? It is, exactly as the relativistic explanation would predict. There are many other reasons like that and tests you can do. It's almost impossible to have photons scatter off of matter without changing their spectrum in some way. And yet the microwave background is a perfect blackbody spectrum, just like it was when it left 14 billion years ago. So Ned Wright, who's an astronomer at UCLA, has a wonderful webpage where he goes through all the different possible non-relativistic explanations of the cosmological redshift and explains why they don't work. So yes, we have thought about it. It doesn't work. Relativity is the right answer. Sam Buck says, more of a personal question here. How do you balance being an extremely smart person with also being kind and generous? There seem to be many people like you who get into schools like Harvard and get jobs at places like Caltech who, after having the world confirm their brilliance, seem to lose the ability to interact with people they view as less intellectually powerful. How do you think you avoided that pitfall, and do you have any advice for people whose academic careers are going really well and worry about falling into this trap? So I almost didn't include this question because, I don't want to talk too much about my brilliance and kindness and generosity. But then I figured, if I can't talk about that or have someone else mention it on my own Patreon AMA, then where else is it going to be talked about? There's plenty of people on Twitter telling me I'm an idiot, so I might as well be able to listen to people who are telling me that I'm smart. Thank you for saying that, Sam, even though I think you're exaggerating a little bit, but that's okay. We'll let you get away with it this time. There is a chicken and egg question here. There are several chicken and egg questions here. So one question is there some truth to the idea that brilliant people who are academically super duper successful are less kind and generous? I would dispute that idea. I think that there are very obvious examples of people who are brilliant and academically successful who are not kind and generous, but there are also plenty of examples of people who are. I think it would be very, very difficult to quantify that, and very, very difficult to really show that people who had reached these levels of achievement were somehow systematically different than other people in the distribution of their kindness and generosity. So there might be a selection effect here that you notice people who are talking down to you, and just like it's easier to notice negative book reviews than it is positive ones if you're a book author. So maybe not. I'm just saying I wouldn't necessarily take that as given. The other chicken and egg problem is, does it come that you start life as a kind and generous person, but then the academic grind wears you down, and by the time you've reached success, you are no longer kind and generous? Or is for those people who aren't kind and generous when they get to success, were they just never like that all along? Right? Is there a causal impact, or is it just a filter that comes? And I think that the filtering explanation works much better than the cause and effect relationship, would be my guess. So if you're worried, as you say, you worry about falling into this trap, I suspect the people who are kind and generous when they're young remain mostly that way. If anything, academic success should allow you to be more kind and generous, right? It's not easier to be generous when you're successful than when you're struggling, right? It's a lot easier to be self-deprecating when everyone thinks you're a genius than when everyone thinks you're an idiot, right? When everyone thinks you're an idiot and you're self-deprecating, it can just be thought of as being accurate, which is a little bit scary. On the other hand, what I do want to say substantively is academia does not select on kindness or generosity. When universities hire people to be on their faculty, they do not say, we want people who are kind and generous. That's just not what they're looking for, especially at the highest level research institutions, which I guess we're thinking about here, where the brilliant people want to congregate, right? They select on brilliance. If you're up for a faculty job at Caltech, they care about your research accomplishments and your potential future brilliance. They almost don't care at all about what good you are as a person. It's really almost kind of remarkable. I hate to air dirty laundry out there, but the extent to which hiring committees could not possibly care less about your personal qualities as long as you're good at doing research would be astonishing, I think, to people in other sectors of the world. Maybe, there's other sort of high pressure, high demand occupations like, Wall Street trader or Silicon Valley or something like that, where they can really home in on ability to do a job at any expense of how good a person you are, but academia is one of those, right? I explicitly remember, different people being considered for jobs at different places. I'm going to be as vague as possible here because I don't want to pick on anybody, but, a person was being considered and someone else said, well, that person's kind of a jerk. And as soon as they said it, everyone's like, who cares? What is their research? I want to know how good their papers are. That's what they care about. So I think it's less that people are ground down by academia or by the journey to being a big shot professor at a big shot institution away from being kind and generous to the people who are hired and promoted, et cetera. It just doesn't matter whether they're kind and generous or not. Maybe they are. That's fine. But we're not looking for that. That's a bonus that comes along. And honestly, to be super duper open about it, teaching is the same way. You can be a good teacher and also a jerk, and you can be a bad teacher and also a good person. But the point is that your ability to teach students does not affect how you're going to get hired at one of these, at like Harvard, Princeton, Caltech kind of places. They just don't care at all. And when they say that teaching is very important to them, they're just lying. It's just false. What they mean is they will occasionally tell their existing professors to be better teachers, but they will never hire people because they're good teachers. That's just not what they're about. That's okay. There are other places that do hire people because they're good teachers. I wrote a whole blog post you can look up called "The Purpose of Harvard is Not to Educate People." That's not a slam on Harvard. The purpose of Harvard, the high level purpose, like forget about you're trying to say it's just a finishing school for the elites or whatever, but the non-cynical purpose of Harvard is to do good research, to do good academic scholarship, and to produce great things. That's the purpose. Students are there to sort of allow that purpose to happen, but the teaching of students is just an afterthought, and that's not even a cynical take. That's just what a place like Harvard is about. There are other universities, other colleges and so forth, where teaching students is the point. But if Harvard switched to caring mostly about teaching students, it wouldn't be Harvard anymore. Maybe that's good or maybe it's bad, but it would just be different. Peter Benham says, laughter is awesome, but really weird if you think about it. Thoughts? No, I do not have any really good thoughts about this one. Is it really weird? I mean, that the statement that laughter is weird implies some sort of pre-existing standard against which we measure whether things are weird or not. Laughter is very natural from some standards anyway, from some points of view. But I bring up the question not because I have anything wise to say about it, but because it's a spandrel question, I think, in general, right? Spandrels being this idea of Stephen Jay Gould and Niles Eldredge and thinking about evolution, that many things that happen according to biological evolution are not necessarily adaptive. Are not necessarily they happen because this particular feature gives us some reproductive advantage, evolutionarily speaking. It might be that some other feature gives us a reproductive advantage and it comes along with this particular feature, or it could just be that the genes that give us some reproductive advantage also have this particular effect. So I don't know whether laughter has some reason for existing or whether or not it is the way it is just because of other physiological things that adapted for good reasons and therefore we're stuck with laughter. But I do hear it is the best medicine for what it's worth. Jacob Yongsma says, is there a way to search for previous questions and answers? Mostly, yes. As I mentioned, there is a website, preposterousuniverse.com/podcast, where you can search all of the previous episodes and their transcripts. Now, for a while, we were doing AMAs that were strictly on Patreon. They were not, transcripts were not obtained for them, so those are not available. But in recent months, for a while now anyway, we've been putting them on the regular website with full transcripts and everything, so you can search there. Vince Corvo says, I'm amazed at your continued patience, but here goes. Is DeWitt's Many Worlds moniker preferred over Everett's original term relative state simply because it's more provocative, akin to Big Bang and Black Hole, but even more so? It would seem that a lot of the hysterical outcry from casual critics could be diffused if the name weren't so scary to little minds. I don't know about that. I have no problem with the name Many Worlds, and I don't know whether Everett had any problem with it. It was not his coinage. His original name for the theory was simply the theory of the universal wave function, which might be the best of them all. I don't like the relative state name because it conveys no information right away. Like if you don't know what is already being talked about, being told it's a relative state theory of quantum mechanics doesn't say very much. And many worlds is okay. It is a theory of many worlds. It's not what I always try to emphasize is it doesn't posit many worlds. All it posits is that the Schrödinger equation and the wave function are to be taken both seriously and literally. And then you get the many worlds coming out. So in that sense, many worlds is not the best name. In Something Deeply Hidden, I originally called it austere quantum mechanics because it's nothing but the wave function in the Schrödinger equation. But that was just a semi-joke because I was never really planning on advocating that we start calling it that. It's just a way of getting into it in the first place. I don't worry so much about the labels, honestly. I wouldn't fret about them. Just try to explain things clearly would be my advice. Luke says, Tim Maudlin writes the following about Einstein and God does not play dice. It has been repeated ad nauseum that Einstein's main objection to quantum theory was its lack of determinism. Einstein could not abide a God who plays dice. But what annoyed Einstein was not the lack of determinism, it was the apparent failure of locality in the theory on account of entanglement. I'd be interested in your take on it and your sense of what the various schools of thought specialties in physics think about it, if they do at all. Well, I don't think that different schools of thought, I'm not exactly sure what you mean by that last part of the sentence. Different schools of thought or specialties in physics don't have individually valuable or precious takes on what Einstein thought, right? I mean, they might have takes that they care about on physics, but I agree with Tim. I think he makes a very compelling case that really what Einstein cared about was locality. I mean, look, Einstein was a very quotable guy. He said a lot of things in conversation, in letters that were not meant for publication, in talking to journalists and so forth, that you can find contradictions of that he says elsewhere. You have to keep in mind, he might have just been kidding. He might have just been joshing around or not wanting to be taken very seriously. Einstein did not go around repeating, God does not play dice, this is crucially important. It was kind of a joke that he said once. Whereas he really was interested in locality. That was the whole point of the EPR paper, that you could not find a locally realist theory. He cared about realism more than anything else, locality second most, I would say. Part of me says, who cares what Einstein thought about? But, it's okay. As a matter of history of physics, it does matter. Now, Tim also goes on to say that John Bell proved, given the experimental data, that physics is non-local, that quantum mechanics is non-local. I think that's not quite true because there's some kind of careful parsing you have to do in the case of many worlds. One of the assumptions of Bell's inequality is that observational measurements have unique outcomes. And in Everett, that's just not true, right? Because in different branches of the wave function, different outcomes are obtained. So strictly speaking, Bell's theorem just doesn't say anything about Everettian quantum mechanics. But is Everettian quantum mechanics local? I think it's a tricky question because as I mentioned already this podcast, I think that there's such a thing as gravity. And I think there is a reason to think that gravity has non-locality in it. So my particular point of view on this question is very different than the mainstream of physics. I think the puzzle is why there is locality at all. Not the puzzle of why there's non-locality at all or how we can deal with non-locality and accept it. Non-locality is perfectly natural. Generic Hamiltonians are non-local. Gravitational effects, especially when you combine them with quantum mechanics, naturally give you non-locality, etc. The real question is why the universe looks even a little bit local. That's what I would like to focus on. Liam McCarty says, on the philosophical foundations of hypotheticals, you often reason with arguments like, if we were Laplace's demon, then. But as you said many times, it's impossible to be Laplace's demon, even in principle. So it seems that any then that follows from if must be moot, and in general, it must be invalid to reason based on impossible hypotheticals. Do you agree? No, I don't agree, because you have to take the spirit. You have to take a statement like that in the spirit in which it is offered. So, for example, if I'm talking about relativity and I say, here's how you calculate the length of a time-like trajectory, and then I say, you can't move on space-like trajectories, but if I draw one, here is the length of it, right? There's nothing wrong with that. There's absolutely nothing that is contrary to logic or scientific practice about doing that, even though we cannot actually travel on space-like trajectories. Likewise, you can make statements, you can make all sorts of counterfactual statements that are impossible in the real world. So when you say something like, if we were Laplace's demon, then, that's just a formulation that is supposed to try to help us understand determinism. That's all it is. It's just a vivid metaphor for trying to appreciate the implications of this idea that there is a certain set of data, information that is specified at one moment of time that suffices to fix what will happen at other moments of time. It's just a colorful way of saying that. Nothing wrong with that. Paul Meggs says, not your particular area of expertise, but I know my 38-year-old son asked me, after reading a really interesting piece on fusion in the New Yorker, Dad, do you think we will harness nuclear fusion in my lifetime? I answered, if by harness you mean useful, I said no. Do you think I was overly dismal or realistic? So there's a little bit I have to say about this. Almost nothing directly answering your question that I have to say about it. So I don't know whether we will harness nuclear fusion in your lifetime, my lifetime, etc. That's an engineering problem. The fundamental physics says there is energy to be released in converting hydrogen to heavier elements. Okay, that much we're sure about. But the whole question of whether or not we can make it practical and get more energy out than we put in is an engineering question on which I am entirely unqualified to talk. The one non-trivial thing I will say is it's certainly been true that we've been promised nuclear fusion as a power source for a long time, and it hasn't come true. So the question is, what do we do with that information? How do we update our credences given that we've previously been promised that this is going to happen and it doesn't? And I would sort of stake out a middle position here. There are some people who would say, look, we were wrong before, but this time we're right. So if we say that nuclear fusion will be giving us more power out than we put in within 10 years or within 50 years, whatever it is, we should believe it. And I think that that's a credible thing to be imagined saying if you have a reason for it. You can't just say, well, but this time we're right because I have trust that the people who are saying it know what they're talking about. It would be much more convincing if you could actually understand why they were wrong the first time and why those reasons do not apply this time, right? On the other hand, I'm not going to agree with people who say, well, we're always promised this once, 20 years in the future, even no matter what date it is, therefore it will never happen. That's not true either. Some things, there's a joke within NASA that there's a universal form of the function of days until launch versus time. You would think that that's a straight line, right? Days until launch goes down over time, 1 day per day. But in fact, launches are always delayed. So the curve sort of goes down linearly for a while, and then it goes up, and then it zigzags up and down because, it bounces up and you go, oh, we're delayed, and then it goes down once a day, up again, etc. But eventually the launches happen, right? And eventually we might very well get sustained nuclear fusion with more power out. I just don't know. So I don't think that the fact we don't have it yet is evidence we won't. And I don't think that optimism is evidence that we will, unless that optimism is based on a clear, explicit understanding of why we were wrong in the past. Frank Lehman says, would you consider yourself a stargazer? Did the night sky fascinate you as a child? Yeah, not that much. I mean, a little bit. I always loved physics, really. I really love fundamental physics. And, that included not only particle physics and gravity, but also cosmology and astrophysics and things like that. And my family, which was resolutely non-academic, non-scholarly, had no idea what particles were, but they knew what astronomy was. So they gave me all sorts of books about, planets and stars. So I read that stuff and I thought it was cool, space travel, science fiction, etc. But it was never my passion. I always want to know the underlying laws of stuff. I was an undergraduate astronomy major, and part of my part-time job was doing not planetarium shows so much, observatory shows, taking people to the observatory and showing them a couple nebulae, a couple planets, a couple binary stars, stuff like that. So there's a brief moment in my life when I could find some interesting things in the sky with a telescope, but that moment is long gone. DLP says, personal advice question. I'm planning to move to a new city to be closer to my romantic partner. My partner is wonderful and things are going very well with them, but I would like to establish a social circle in the new city that's not connected to them. Do you have any advice for making new friends in one's 30s outside of a shared work or academic context? So, short answer, no. I don't really have any great advice. I don't think that this is something that is subjectable to an algorithm. You know what I mean? In other words, I don't think that there is sort of a strategy that you consciously adopt to make new friends. You can certainly try harder or try less. I mean, that's the one reason I wanted to answer the question, just because the non-trivial thing I can say is if, depending on what your personality is like, it is certainly possible to just either stay home or go to work and don't live. Those are the only elements of your life, right? And then you're not going to make other friends unconnected from people at home and at work for obvious reasons. So much like for romantic advice, which I know is not what you're looking for, but the same principle applies, that you do have to put yourself out there a little bit. And even though the stakes are much higher for romantic connections than for mere friendships, the same kinds of jeopardy apply in the sense that you can embarrass yourself, you can look bad, you can say awkward things that you regret later. I mean, maybe the chances are lower if you're just trying to small talk with potential friends, but they're still out there. So I get that, again, depending on who you are, if you're a very gregarious, extroverted person, this is not a consideration. But for some people, just going to a party where you don't know many people is hard, is fraught with peril, and I get that. But after you asked your question, I thought about the friend circles that I have with my wife, Jennifer, in Los Angeles. And, it's a very heterogeneous collection of ways in which we met them. I had some friends just from work. When Jennifer moved in, she had almost no friends directly in LA. And since then, she's made plenty of friends who she's closer with than I am, etc. Many friends we actually first got to know online in one way or another, either, on social media or by, emailing or being connected with other friends, things like that. And other people we just met at random events. Really, that's why I'm skeptical of the algorithmic approach. One of our very best friends we met because we had another friend who had been connected to us by a third friend, and this person was leaving town and having a party, so we went to their goodbye party. And once we arrived at the party, this woman comes up to us and says, "Everyone here is accompanied by small children. It looks like you are not. Please talk to me." And we bonded over that. And many times that will happen, and then you'll never see them again. In this case, we became very good friends. So I think it's unpredictable. I think that that you need to go through a lot of people before you find ones you really connect with, and go through a lot of people who you are not going to end up being friends with, and keep trying, keep putting yourself out there. That's the only tangible advice I have. Napoleon's Corporal asks a priority question. The simulation hypothesis has come up in several episodes, and I believe that one of the reasons it has come into vogue is the relatively recent finding that much of the reality that we experience, that we used to think of as continuous and flowing, seems to actually be discrete and granular. Light, time, and even space itself are evidence strongly suggests this way. The idea that reality is a consciousness-driven digital construction rather than a simulation has its followers and some very persuasive arguments to support it. Given that there undeniably is something rather than nothing, it is the simplest explanation. The initial Big Bang theory was seductively simple and intuitive, but when cosmic inflation and quantum theory reared their ugly heads, that simplicity went right into the dustbin. Is it really likely that the something that has always been is so incredibly arbitrary and contrived? Yet I rarely see this concept openly discussed and seriously considered. My question is, why are serious scientists so reluctant to consider this perspective? So, unfortunately, even though this is a priority question, I think that you phrased it a little bit badly, because it's a long question, and then by the end, you say, I rarely see this concept openly discussed. Why are scientists reluctant to consider this perspective? But I'm not entirely sure what you're referring to by this construction, this concept, this perspective. I think you're referring to the idea that reality is a consciousness-driven digital construction rather than a simulation. So there's separate responses here depending on whether you're asking why don't we take the simulation argument seriously versus why don't we take the construction, consciousness-driven digital construction seriously. So first, I think that I don't know exactly what you mean, but I would completely disagree with the idea that we have recently discovered that reality is discrete and granular or pixelated. I don't know what you're talking about there. The best understanding we have of the fundamental nature of reality is as a quantum field theory, which is resolutely non-discrete. It's completely continuous. Quantum mechanics in general is continuous. There are observables that are discrete, but that is exactly the observability of them that is discrete, not the underlying reality. So I'm not quite sure what you're referring to about the evidence strongly suggesting that light, space, time are somehow pixelated. Second, on the simulation argument again, I think a lot of physicists don't pay attention to that just because it's not answering a question that we have as a pressing issue, right? I think that a lot of physicists would say, yeah, maybe it's true, maybe it's not. I have no way of knowing, and it doesn't help me understand the world that I see. So I'm not going to care that much. I think that's the major reason out there. Without adjudicating that right here, I would say that's what is in the back of the minds of most scientists. So you're specifically, but I think what you're asking about is the specific idea that reality is a consciousness-driven digital construction rather than a simulation. So again, I'm sorry, I have to disagree with everything that you're, all the assumptions behind this theory. For one thing, quantum theory is not arbitrary and contrived at all. Quantum theory is incredibly simple. The problem, as I see it, is that it is too simple. The idea, if you really believe in an Everettian inversion, where all you have is a wave function and the Schrodinger equation, all of the effort goes into teasing out the implications of that simple idea. But the underlying idea is literally almost as simple as it is possible to imagine an idea being, while having a chance of understanding our world. So to say that it is incredibly arbitrary seems way off base. Likewise, for cosmic inflation, which is a completely different kind of theory than quantum theory is, it simplifies things. We had a bunch of facts about the universe. The original motivation for inflation was the universe was spatially flat. It was very homogeneous on very large scales. Then there was also the thing that there were no monopoles, and there became the issue of the origin of structure. And all of these disparate things were explained by this one simple idea of inflation. So to say that, again, that it's arbitrary and contrived doesn't seem accurate, but also we don't know whether inflation is true. So it's very different than quantum theory in that sense. Finally, I don't know much about what you mean by the idea of a consciousness-driven digital construction. But as soon as you use the word consciousness, that's when I'm going to say, now we're talking about something that is incredibly complicated, incredibly ill understood, right? I mean, it's obvious that consciousness is not very well understood. It is much less well defined than relativity or cosmology or quantum mechanics or anything like that. It's a conceivable hypothesis that you're welcome to consider and think about. But the idea that right off the bat saying that reality is a consciousness-driven digital construction is somehow simpler just seems completely wrong to me, completely backwards. I think that it might give the appearance of simplicity by virtue of being ill-defined, because it's only vaguely specified what you mean by consciousness. You can say, well, this explains all the things I want to explain. But a good scientific theory is not just stated in a small number of words, but is unbendingly precise, right? A good scientific theory says, this thing is an element of this mathematical space which evolves according to this equation, right? It doesn't just say consciousness, or it doesn't even just say physics or stuff or material, right? There's a very clear mathematical structure that is making predictions. That's what we mean by a theory that is simple and compelling. It doesn't mean it's true, but the theories that have been very successful always have that form so far. Brad Malt says, in the September AMA, you answered a question about whether there is a branch of the wave function where the Germans won World War II. You said yes, but we should take comfort in the knowledge that this is a very thin branch, which I understand to mean the probability of anyone ending up on that branch is small. But does thin have any meaning after the world has branched? Suppose that there are two possible outcomes in superposition, one with 10% probability, one with 90% probability. Once decoherence occurs, there are just two branches and I'm on one of them. Hasn't the meaning of thin and thick gone away? Yes, absolutely, 100%. Once you're inside a branch, the thickness of the branch is completely unobservable to you. The idea of thickness and thinness is only relevant. Sorry, I might have misspoke. Thickness and thinness is only relevant when we're comparing different branches from some kind of God's eye view. But that's exactly what we're doing when we're talking about a branch where the Nazis won World War II, right? I mean, we're not in that branch. To the people who are in that branch, that's their reality. That's absolutely real. The fact that it's a thin branch doesn't matter. But if we're comparing all sorts of branches to each other, that's when the thickness or thinness matters a lot. Josh says, it makes sense to me that GR predicts divergences from Newtonian gravity, such as gravitational lensing. What I don't understand is why it predicts divergences when it comes to the motions of bodies such as the anomaly in Mercury's orbit. Can you explain why GR and Newtonian gravity predict different behavior in this case? So I did not do what I should have done here, or what I would have done if this were a different situation, and gone back to my GR book and re-gone through the derivation of the precession of the perihelion of Mercury. I remember what you do. There's an effective potential you define. There's a new term in that effective potential that goes as 1 over r cubed instead of 1 over r squared, which is the inverse square law for Newton. So there's a technical answer, but that's probably not what you're looking for. So there is definitely a sort of hand-wavy answer to why there are differences at all between Newtonian gravity and general relativity. In Newtonian gravity, there's a very simple geometric reason why the force of gravity is 1 over r squared. Namely, you can think about lines of gravitational force extending out from the gravitating body, like the sun or whatever it is. And these lines never end. They don't have, I should say they only end on gravitating bodies. They do not dilute away or disappear in empty space. Okay, they only end on matter, on a source for gravity. So if you have just one spherical body and empty space around it, there's going to be lines of force radiating away from it, and those lines are going to dilute away in number density as the area of a sphere that you draw around that body goes up. And guess what? The area goes up as r squared, as the distance of the sphere, the radius of the sphere squared. That's why you get an inverse square law in Newtonian gravity. In general relativity, that's almost true, but there's a new effect that comes in, which is that there's a field theory in general relativity, a propagating field, and that field interacts with itself. If you want to think about it in the language of particles, which you don't need to do, it's just classical relativity, but if you want to think about it in the language of particles, it's as if gravitons in general relativity interact with each other, because gravitons themselves have energy, and gravity couples to everything with energy, even to other gravitons. Whereas in Newtonian gravity, there's no gravitons at all, but gravity does not interact with itself. The gravitational field in Newtonian gravity is not a source of gravity, whereas the gravitational field in general relativity is. So when the gravitational field becomes relatively strong in general relativity, we expect it to deviate from the Newtonian prediction because there's an extra source of gravity, the gravitational field itself. And Mercury, of course, is not only relatively elliptical compared to other planets, it's the closest to the sun. It's feeling the strongest gravitational field. So that is where you would first expect the deviations from perfect linearity to show up. Now, having said all of that, let me footnote that by saying everything I just said is true about general relativity versus Newtonian gravity. I am not sure that is the most accurate explanation exactly of the precession of Mercury. So that's a slightly different question. It's a related question, but there could be like a simpler, more geometric way of talking about the precession of Mercury that I'm just not aware of right now, so I'm not giving it to you. But what I said about the difference between GR and Newton is definitely right. Rob Butler says, I've often read that black holes will eventually dominate the entire landscape of the universe until they too evaporate. In your episode with Priya Natarajan, she described the formation of supermassive black holes as predominantly events of the early universe, and also that although massive, they are a small fraction of a galaxy's total mass. Given galaxy mergers, ejections of stars from their host galaxies, all that stuff, is it possible that the aging universe might comprise many wandering objects instead of its often described destiny as a sleepy neighborhood of postprandial black holes? Well, I'm not a super expert here. It is completely possible. In fact, I think it's almost certainly true that it's not going to be everything in the universe that converts to black holes. There are, for instance, in our galaxy, our galaxy has a lot of stars in it. Forget about the dark matter for a little while, but imagine the galaxy is a collection of stars. Stars interact with each other gravitationally. Occasionally, there are close encounters between two stars moving along different trajectories. And as we discussed earlier in the AMA, there can be a slingshot effect. Momentum from one star can be borrowed by the other star, and it can be ejected from the galaxy. This is a general feature of just Newtonian gravity, that mutually gravitating collections of particles will spit out occasional particles that just become unbound and go away forever. So that's going to happen. So there will be wandering stars or planets or rocks or whatever in the universe. But I think that most stuff in the universe will stay connected to a galaxy. And the trick is you have to wait a long time, right? You're talking about very, very long time scales here. So it is true that in our Milky Way galaxy, for example, today, the supermassive black hole at the center is a tiny fraction, 0.1% or whatever it is, of the total mass of the, probably much smaller than 0.1% of the total mass of the galaxy. But just wait. Things fall into the black hole and they don't come out, right? So the point is, if you just wait a very, very long time, eventually all that stuff is going to fall into the black hole. And the question is, which happens first? Does all the stuff fall into the black hole, or does the black hole evaporate away? And I think that, within some reasonable set of parameters, most of the stuff inside a galaxy will fall into the black hole before the black hole evaporates away. That's why we think that there will be a long period of the universe's history in the future where it will be just sleepy postprandial black holes. Carlos Nunez says, Today, a very dear family member died. Have you ever had anyone close to you die? And if so, how have you dealt with the loss? So I'm very sorry to hear that, Carlos. I know it can be very hard. Yes, I've had people close to me die and members of the family and things like that. Once you reach a certain age, it's almost inevitable. And it's never easy, right? It's a hard thing. Even as convinced as we can be that it's going to happen, when it actually happens, it's tough. And it's tough in part because, both because we remember having them with us and because it's inevitable to imagine alternative futures where they're still around, right? And that's better. Those futures are better, and so we're in one of the bad futures. I don't have any really strong, again, techniques or algorithms or whatever to dealing with this kind of loss. One thing is it will absolutely take time. There's no shortcut. That I know from experience, personal and with other friends. And the closer the person is who dies, the longer it will take. And there's no rushing it. I mean, there's things you can do that, make yourself more healthy and dealing with it, et cetera. But you can't just shortcut the process. The process of grief is of adjusting to a new reality, and that just takes time. And there's a continuous, you're still living your life. There are things that are happening to you in your life and that you need to think about, et cetera. And eventually you will almost always come to an equilibrium where you accept that this person is no longer around and you're living a different kind of life. And you're still sad that they're gone, but that sadness is not front and center in your consciousness. But in the immediate aftermath of the event, it might very well be front and center, and there's nothing wrong with that. It's completely okay to grieve and to be sad about it. It's not like your sadness is somehow a mistake or a failure. Let me say one thing, which I don't know whether it's relevant or helpful or anything, but it was very striking to me. At least once, someone close passed away, and there were members of the family and inner circle who were very religious, and there were members who were not. And the people who were not religious uniformly handled it much better. And I don't think that that's necessarily generalizable. I think it might depend on those particular people and the particular way they were religious, et cetera. But it spoke to the fact that acceptance matters. And in some sense, the religious people really genuinely believed that the person would die and go to heaven. And the non-religious people thought that was the end of their existence. But somehow it was more acceptable to believe it was the end of their existence. It wasn't hanging on, right? It was a leaping into the new reality where the person no longer existed. And that was easier than the sort of halfway house where you think, well, a version of them still exists, but I don't have access to that person or whatever. Again, I have no data on whether or not that's generalizable. Whether or not it's just these individual people, et cetera, et cetera. But maybe it suggests that part of the process of acceptance and dealing with it is real acceptance, right? Really accepting that whether you're religious or not, for you, they are gone. It's not an easy thing to think, but I mean, maybe the non-religious perspective anticipates it more fully, right? Like you have a finite lifespan. We have 3 billion heartbeats on average. That's how much we're all going to get, with a big error bar there. And that makes the moments you have here on Earth all the more precious, in my view. Again, nothing wrong with grieving, no way to hurry it up that I know of, but you do deal with it. It's just like we talked about with the species and ecology before. Life is flux. Life is changing. Life is undergone in a set of different conditions from moment to moment. And the trick of life is not to find the perfect conditions and stay there forever. The trick of life is to adapt and adjust to the conditions that you're in while also trying to improve them. It's a balance that you have to keep up forever, for as long as you live, I should say, because you don't live forever. Nicholas Weiberg says, how can we distinguish between black holes and other massive objects such as neutron stars by observations? Apologies for the whiplash of going between very, very different questions from topic to topic here, but that's the nature of an AMA. Sorry about that. Anyway, how can we distinguish between black holes and other massive objects such as neutron stars by observation? Perhaps our best theories predict that dense objects beyond a certain mass must be black holes. But what if the theories are wrong? For instance, could the object at the center of our galaxy actually be a massive neutron star? Yeah, it's always possible our theories are wrong. And I think that it's not a yes-no question. I think that there are different ways our theories can be wrong that are more or less plausible. So, again, astronomers have absolutely wondered about this. How do we know if it's a black hole? And as you say, there's a theoretical prediction. If something is a certain mass and a certain size, then it has to be a black hole, but maybe the theory is wrong. What you can do, so there's two steps. One thing that people try to do is just to say, again, what I sort of implicitly included already, you simultaneously measure not just the mass of the thing, but the size of it, right? And at some point, if general relativity is roughly right, then if the size of the thing is smaller or as small as its Schwarzschild radius, there's literally nothing else it can be other than a black hole, if general relativity is roughly right. So that has nothing to do with our theories of matter or pressure or equations of state or any of that stuff that go into neutron stars, et cetera. It's a pure general relativity question. But of course, general relativity can also be wrong. So the slightly more sophisticated thing that people try to do, which is also harder to do, is to think about the emission of light from different objects. So typically objects, or not typically, but often, these objects will have accretion disks around them. These accretion disks are radiating, and they have a small object at the center, nominally a black hole. And so what you can try to do is to say there's so much radiation coming from this accretion disk that the thing that is in the middle would glow if it were not a black hole, right? You're heating it up. And you can try to sort of put limits on the size of the thing versus its luminosity and stuff like that. All that is a lot more hand-wavy, a lot more to do accurately, but we try. At the 100% confidence level, you'll never be sure unless you can go up and look at the thing. So, but honestly, having said all that, that's all very, very careful and very precise and correct, but they're black holes. Trust me about that. There's not a lot of, there are some edge cases where the evidence isn't that good that they're black holes, and maybe there's something interesting. But for something like the center of our galaxy, there's not a lot of plausible alternatives other than a black hole. Seamus McLennan says, given unlimited resources, is there an experiment you would like to conduct or have others conduct in any branch of science? This could include the theoretically possible, even if not currently technologically possible. It's a good question, but I don't have a great answer to it in the sense that, as I was thinking about it, here's the problem. The thing about experiments, especially interesting ones, is you don't know what answer you're going to get ahead of time. So I have things I would like to know, but I don't necessarily have experiments that will clearly give me the answer to them, right? I would like to know why the Higgs boson mass is so much lower than the Planck scale, the hierarchy problem of particle physics. We were hopeful that the LHC would tell us that we would find some particles with similar masses to the Higgs boson that would help us work out why its mass was so low. But we haven't yet. Maybe we will the next round of the LHC, but we haven't yet. You could, the obvious thing to say is let's build a particle collider with Planck scale energies or super Planck scale energies, and then make it a sufficiently precise one that we can really just find every single particle that exists below the Planck scale. That's probably the answer I would give, but we have to be open to the fact that even that wouldn't give us the answer to this question that we're asking. I'd like to know what the dark matter is, but there's one kind of experiment that would find the dark matter if it's a weakly interacting particle. There's a whole other kind of experiment that would find it if it's an axion or something like that. So it's very hard. Even if we had unlimited resources, it's hard to say what is the one experiment that would really help us out. That's why we have to do all of them. Jeff B. says, do you think that finding a subject to be a chore to learn is a sign that we should spend our time doing something else? You said it very well. There are things that it would be fun to have already learned, but the process in getting there seems much less appealing. Should we only spend our time doing things that we find enjoyable, or is it worth it to sometimes grind to get a new level of understanding? So 100%, we have to sometimes grind. We have to sometimes do chores. Look, when you're learning general relativity, it's one of the most interesting subjects in the world, but there are all these Greek indices all over the place and these covariant derivatives with a lot of tensors flying around, and there is no way to get around tedious manipulation of them before it becomes second nature. If you want to play basketball, you got to shoot a lot of free throws. You got to practice. If you want to play the piano, you got to do scales, right? All of this stuff. If you want to learn a new language, you have to memorize vocabulary and practice your grammar. Of course, that's just always a part of the process. There is no royal road to geometry, as Euclid is purported to have said. Yeah, I hope I did not give any other impression. There's a bigger picture question. If you find an entire field to be mostly chore, then should you switch to another field where it seems like a lot more fun? That's a more difficult, subtle question. But within any one field, I think that most of the activity that is necessary to learn that field in the first place, and maybe even most of the activity to produce something useful within that field, will be by itself a chore that is part of a bigger achievement that you get along the way. Johnny says, I've heard the term fiber bundle used a lot. Is it possible to explain what that is with mere language, or is it one of those things that require math to make sense of? So I don't know where you're hanging out, Johnny, where you hear the term fiber bundle used a lot. It is very common in both mathematics and physics. When we talked before about gauge theories, fiber bundles is the setting where gauge theories is. That was not great grammar. Gauge theories are set in the context of what are called fiber bundles. It's actually not that difficult. Think of it this way. When you have quarks in the strong interactions, you might have been told that quarks are either red, green, or blue. There are 3 colors of quarks. That's not exactly true. Of course, it's not exactly true. But it's not only not exactly true because they're not really the colors, but also because it's not just there are 3 kinds of quarks. There's a 3-dimensional space of quarks, a 3-dimensional vector space. So just like real space, where it's up, down, left, right, forward, backward, 3 dimensions, there is a vector space where the quarks live. And that vector space is 3-dimensional. So it's not that quarks are either red, green, or blue. They are some combination. They are a vector in red, green, blue space, okay? Every quark is like that. And the point is that the gauge symmetry is simply the symmetry that it doesn't matter how you orient your axes. I called it coordinate variance before, but it's the same idea. You can orient the axes you call red, green, and blue however you want. That is literally the symmetry underlying the strong interactions. And the fiber bundle comes in because when you think about these quarks are fields, right? There's a quark field, up quark field, down quark field, anti-quark fields, etc. So at every point in space, there's a quark field. And this quark field takes the form of a little vector in this 3-dimensional color space. That's what a fiber bundle is. A fiber bundle is just some vector space, or it doesn't need to be a vector space, but some kind of mathematical space, one of which is attached to every point in space-time, or more generally to some underlying manifold that you might care about. So you can have things like circle bundles. So instead of a vector space, you have a circle at every point in space. In fact, there's some clever way that you can think of the 3-dimensional sphere as a 1-dimensional fiber over a 2-dimensional sphere. I know that none of those words are meaningful in any way, but the point is that there are examples that are not vector spaces. Fiber bundles are just generalizations of the idea that you can have vectors at every point in space. That's all it is. Different kinds of vectors, different kinds of non-vectors at every point in space. And then you need to talk about how the vectors or other things at different points of space are related to each other. And this requires the idea of what you call a connection on the fiber bundle, which tells you how to connect the values of fibers at nearby points. I talk about this a little bit in the biggest ideas in the universe in the gauge theory section, or in the symmetry section, maybe. But I don't call them fiber bundles. That just seems superfluous language. I hope that made some sense. That's as much as you're going to get from me right now. Ken Wolf says, when listening to your conversation with Chiara Marletto on constructor theory, the idea that this methodology could be applied both to particle physics and to higher-level emergent behavior reminded me of the scale-free behavior you had discussed with Nigel Goldenfeld in your previous episode. Do you think there's any possible link here, or am I conflating 2 completely different ideas? I think they're not connected. This is my guess, and I say that only very tentatively because maybe I'm missing something. When we were talking with Nigel about scale-free behavior, we were talking about a single kind of system which can be analyzed on different scales, right? So when you have the Ising model, right, a bunch of little spins that have some orientation, either up or down, you can sort of chunk them up into domains. You can look at one spin, or a 2x2 array of spins, or a 3x3 array of spins, or a 4x4 array of spins, and you can ask about average properties in each of those chunks. And then you could ask how the statistics of those properties change. So when I look at each individual spin, how many of them are up, how many of them are down? When I look at 2x2 arrays, how many of them are all up, how many of them are all down, how many of them are in between, etc. And the idea of scale-free behavior is you get roughly the same behavior no matter how big chunks you make. So if you have, for example, if you're at a very low temperature, what that means is all the spins want to line up. So you do not get scale-free behavior. What you get is all the spins are lined up. So if you have all of the spins, they're doing things, and that's interesting. But then if you have a block of spins, you learn nothing new, because they're all lined up. Once you know one spin, you know all the other ones. Whereas if you have fluctuations, and so on the other end, on the other side of the limit, if you have super high temperature, then knowing one spin tells you nothing about any of the other spins. So there's no structure in looking at larger and larger chunks either. It's in this in-between critical regime where there's interesting information on every scale. So in other words, the correlation length at zero temperature is infinity. One spin is correlated with all the other spins. The correlation length at infinite temperature is zero. And at in between, there is some interesting correlation length. So that's all about a single system looked at in different ways. What Chiara and I were talking about is different kinds of systems, right? And also, what she wants to investigate is the idea of a single methodology or perspective on how we formulate laws of physics that could be applicable to different kinds of systems. It's not a statement that the behavior of those systems is the same or even related to each other at different scales. It's just the way that we can think about the laws of physics rather than being a Laplacian kind of picture where you give me initial conditions and then solve for equations. Instead, you ask about what things are possible and what things are not possible. That framework, that paradigm, that approach might be applicable to a wide variety of different phenomena. It's not necessarily part of the picture that the phenomena be physically related to each other or have similar behavior at different scales. It's just the similar language for describing that behavior. That's why I think that they're not necessarily related. It's a different kind of comparison. But again, maybe there's something lurking there that I'm not really aware of. Sekar Rabala, I guess, let me say one more, slightly more definite thing there to Ken's question. There are absolutely examples of emergent behavior which are not scale-free, right? Scale-free behavior is somehow special. A classic example of emergent behavior which is not scale-free is, we've just been talking about quarks and the strong interactions. Above a certain energy, quarks are free. Quarks and gluons just fly around all by themselves. There is a definite energy, a definite scale, the QCD scale, that separates that kind of behavior from the kind of behavior we're familiar with in the low energy world, where quarks are confined into protons and neutrons or other kinds of hadrons. So there's not scale-free behavior. There is a definite scale on one side of which things act one way, and on the other side of things on the other side of which things act the other way. On one side, the natural language to use is one of quarks and gluons. On the other side, the natural language to use is one of baryons and mesons, okay? So that's a very common emergent kind of property. The scale-free behavior is a little bit special. All right, Sekar Rabala says, I have a process-related question for you. You cover a lot of interesting topics with a variety of guests. My question is, how do you decide which topics and how do you decide which guests to invite for the topics you want to cover? It's a combination of both. Sometimes I pick a topic first and then go for a guest. Other times a guest just seems really, really good, so I go grab them. And it's a very haphazard thing. This is the anti-algorithm AMA episode. There's no algorithm for me finding the guests or the topics. It's stuff I'm interested in. I do want to keep things lively intellectually. So I want to mix things up. I want to have, if I don't want to have 3 physicists in a row, and I don't want to have 3 economists in a row, or 3 novelists in a row, right? I want to have a variety of things from week to week. I want to keep you all guessing what's going to happen next. And I think that's fun for me. I'm not interested in every single topic out there. There are some topics that I'm just not that interested in. And I'm not that interested in... Well, look, I get a lot of, once your podcast gets to a certain level of recognizability, you get a lot of pitches. I get a lot of emails from people who would like to be on the podcast, mostly not from people themselves, sometimes from people themselves. And again, I've said this before, that's fine. You're welcome to suggest yourself as a guest on the podcast, as long as you are not insulted if I say no, right? Maybe it's just not a good fit. But I get a lot of pitches from PR agents or from media people at publishing houses when people have books coming out. And there are a lot of books on self-help. And I don't mean like, be happier. It's more like, be happier is part of it. Be more successful. Here's your algorithm for finding success or for getting books written or for improving your health or stuff like that. Oh my goodness. So many of those. I'm not that interested in those that much. It may be the case, like it was the case with Leidy Klotz recently, for example, that there is some interesting scholarly point about the universe which can then be used to help you live your life. His point was human beings have this prejudice, this bias, when we look at designs for improving them by adding things rather than subtracting things, okay? And there's sort of neuroscience and psychology behind that, as well as engineering theory behind that. So that's intrinsically interesting. It may also suggest ways that you could improve your own going through life. I hope that occasionally podcast guests tell you things that might help you get through your life. But that's never the primary point for me. The primary point for me is, are we illuminating some aspect of how the universe works? And for those purposes, I take the universe in an extremely broad sense. So you're part of the universe. Politics is part of the universe. Religion is part of the universe. Music and art are part of the universe, etc. But it's that scholarly, intellectual, let's figure out how stuff works that is driving me. And within that, I'm looking for a very wide variety of guests. And also, young people, old people, people from different fields, all that stuff. Diversity along many different axes. Edward Morris says, could you please comment on the concept of imaginary time? I'm wondering if it's just a convenient mathematical trick, or should it be more than that, like a clue to some deeper truth about the nature of time itself? Nope, it's just a convenient mathematical trick. As far as I know, all of my experience, and I do have experience, I've written about it, etc., it's just a trick. And it's not even just for general relativity. The origin of imaginary time actually comes from what is called the WKB approximation in quantum mechanics, from early explorations of quantum tunneling. It's just a trick. There's lots of tricks, and then it takes on a little bit more of a reality when you translate it into words. Don't fall for that. Just a trick. John Morgan says, you clearly have a ton of experience debating complex topics in a thoughtful way, and I really appreciated how that's allowed me to reconnect with my physics education through your podcasts. I'm curious about your strategies for handling topics with more personal stakes and passion. For example, debating a controversial politician or the merits of obtaining a COVID vaccine with an intransigent relative. I have difficulty keeping my cool, which immediately craters my ability to think coherently. This doesn't just have implications for personal lives, because for folks in a leadership position, we sometimes face hot-button issues which present challenges while navigating the complexities of setting an example, maintaining an inclusive environment, etc. Yeah, so I completely appreciate the issue that you're bringing up. It's a very important one, it's a universal one, and it's a difficult one. I think that the fact that you recognize the issue is 98% of the solution to the issue. There's no easy solution. Look, we all have emotions, right? We all have biases. We all have immediate visceral reactions to things, especially when we think people are being dumb or when we think people are being evil, right? This gets our hair rising up and it gets our blood boiling, or whatever metaphor you want to use. That shows up, whether it's in real life or in social media or whatever. And it will always show up. And a lot of people don't want to deal with it. A lot of people like it, right? There are people who seek it out. They get kind of an endorphin rush from arguing with people in a passionate, heated way. Other people sort of I would say, kind of effectively act that way, while remaining, for all appearances' sake, to be level-headed. Like, they remain level-headed, but they say things that drive the conversation downward rather than to a more elevated plane. So sometimes you want to give in. Like, the emotions are not entirely bad, but I take the point of your question. We would like to be the good examples, right? We would like to be the examples of thinking things through carefully, of listening to other points of view, to being the voice of reason. And I don't always succeed at that, for goodness sake. I certainly know that I would aspire to do that, but I don't always succeed. And I try. So my point is, trying is most of the battle. Well, it's not even most of the battle, but it is the single most important thing that you have to put into your toolbox of strategies. If you are reflective, if you are self-aware and cognizant of what is going on, you'll be able to say to yourself, I wasn't quite as calm and rational that time as I should have been. What can I do to be better next time? And I think that's, I try to do that. I try to get better. Plenty of examples of things I've done and said in the past where I was too quick and too glib, made things worse rather than better. Trying harder is already puts you in the top 2% of interlocutors in this particular aspect. Other than that, I guess the other thing is to recognize and correct for our innate tribalism, right? It's a very natural human thing to divide people into teams, our team and the other team, and to conceptualize things as a competition. And then once you do that, once you slip into that mode, your goal is to win the competition, right? Not to reach mutual understanding or, just discuss things and learn more, et cetera, et cetera. If somehow you can recognize when that happens and correct for it, if even with people you deeply, deeply disagree with, you can have an attitude of mutual learning, then you'll be fine. And it sounds hard to do, and it is even harder than it sounds because some people aren't going to be reasoned with. They're just not. I mean, they are either evil or dumb or whatever. People like that exist. So it's not just you should always accept the point of view of everybody else. Some people's point of views are not worth accepting. But probably a lot more people's are worth listening to than we do in real life. We probably err mostly on the other side. So in that case, I would just disengage. I try to organize my life so that I have to put up with people like that as little as possible. I block a lot of people on Twitter, for example. You may have heard me mention this, and people are sometimes like, wow, why'd I get blocked? Aren't you in favor of free speech and whatever? No, I'm in favor of you being able to tweet. I'm not in favor of me having to listen to you no matter how annoying you are. If you're annoying, even a little bit annoying, why should I listen to you? Why should I have you on my Twitter timeline? I don't want that. It's not a matter of not listening to other points of view. Other points of view can be said in non-annoying ways, right? In non-confrontational, non-insulting ways. But if the way that you're going to say things is just dumb or annoying or intentionally trying to start an argument, etc., without giving good rational reasons, I'm not learning from that. I'm just being annoyed by it, and you're gone. Harder to do with relatives and people who we care about, etc., but ultimately I think that people don't do that enough either. Okay, Varun Narasimhachar, sorry for getting your name mixed up a little bit. Varun Narasimhachar says, what is your attitude toward the traditional values of honor and valor and their role in defining the conventional ideal of masculinity? The challenges faced by humanity today call for solutions that involve inclusivity, cooperation, and nuanced dialogue across tribalistic boundaries, as we were just saying, by the way, which to a first approximation conflict with the honor-value system. I have seen many people, especially men, lament at the emasculation of culture in this way. In my mind, they are just clinging to a value system that had relevance in traditional human societies, but doesn't anymore. I also think that the sentiment mostly comes from male insecurity. Do you agree, or do you think that we must take such concerns seriously and incorporate those traditional values more into contemporary human life? I would say I kind of largely agree. What I certainly agree with is that our existence as human beings is in a very different context now than it was just a few hundred years ago, much less thousands of years ago, right? Our environment in which we live in is a very different place. And that might very well call for different values and different organizations of society, and treating women and people of other races and ethnicities and sexualities and abilities in a different way, in a more inclusive, positive way, is something we can do now much more effectively if we choose to do so than we might have been able to do in the past with different constraints and scarcity and economic deprivation and things like that we had to deal with in the past. I'm not excusing bad behavior in the past, but simply at the level of explaining it, you can see why certain inequities and certain hierarchies evolved in the past that now we don't need anymore. Right? That now we just don't have the same motivations or same justifications or same original reasons for them to exist anymore. Okay, so in principle, I'm open to the idea that our set of values, whatever they are, might need to be updated from what it was 1,000 years ago. And in particular, notions of masculinity and femininity are obvious examples, right? I mean, the traditional roles of men and women are, what I should say is the current roles that men and women have in the world are very far away from what they traditionally were, right? Whether it's giving birth and raising children or having jobs or any of those things. So a complete rethink wouldn't be out of place. Having said that, I think that when you just say honor and valor, when you separate that from issues of femininity and masculinity and just ask about those questions, those are, I think, perfectly good values. Honor is a good value. Valor is a good value. I mean, maybe the natural or at least commonplace conflation of those values with masculinity is misplaced. But I think that something called honor is a good thing. Again, any value can go too far. You can take honor too strongly, or you could misconstrue it, or you could implement it in a counterproductive way. But the idea that I try to be an honorable person, I try to keep my promises, I try to fulfill my responsibilities, I try to do a good job and not let people down, and other things that are typically associated with the idea of honor or even valor. You could make a similar list about valor. Yeah, these are generally good things. And I think that's usually good. I think that if you listed traditional positively associated values that are traditionally associated with either men or women, they're usually all good, right? Being nurturing, being loving, being communicative, whatever the traditional female values are, those are also good. And maybe those are not, I think that the real issue is that because we're in flux, right? Because society is changing in ways that, it's a pretty rapid change in how we live our lives compared to previous years, previous generations, previous eras. People are left behind a little bit, or, people still taught old ways of thinking or valuing, even though the world is changing around them. And that leads to a lot of mismatches between what people think they've been taught about what they're supposed to do and how they're supposed to live and the world they find themselves in. And I'm actually pretty sympathetic to people who are struggling with that mismatch. Like, I might think that a certain person is acting badly, but if they're acting correctly according to a certain value system, then I'm not going to say they're acting correctly by my value system, but I'm sympathetic to the fact that they're trying their best according to their value system. And what we should do is talk about it. We shouldn't just judge them badly and condemn them. We can condemn them, but it's better to try to reason with them, try to explain why a more traditional understanding is not appropriate in this particular example. And this is all mixed up with other problems, other issues that are kind of not the same issue, but they become involved with it for other reasons, right? Like a lot of people who will try to defend and advocate for a more traditionalist view of honor and valor and masculinity have other agendas and are using these words to, get sort of positively balanced vocabulary associated with whatever their real goals are. So I'm not going to go into too many details about that because I'm sure it's very different in different circumstances, but something to keep in mind that if a particular person you disagree with is using this word, it might be the person's fault, not the word's fault. Amanda Bradford says, has being born and raised in the Philadelphia area influenced your personality? Yeah, probably not too much. So, I mean, two answers to that question. My first instinct is to say no, probably not too much. In part because I grew up in the suburbs of Philadelphia. I can't even claim to be really, inner city Philadelphian. And also, yeah, I mean, partly because I think that people overrate the extent to which different cities or different locations within one country are really different from each other. Like, Boston and Philadelphia will tell you stories about how different they are, and they're not that different, really. On the other hand, if I'm a little bit more honest and self-aware, everyone tends to think of wherever they grew up as just normal. It's like everyone else is judged in comparison to me. It was slightly hilarious for me to watch Kate Winslet in what was the TV show? The TV show I'm talking about that was set in the Philadelphia suburbs. Mayor of Easttown. Yes, Mayor of Easttown, because that wasn't quite my accent that they were speaking, but I certainly had friends who talked in that accent. It was a nearby accent, the Easttown, that's sort of just west of Philadelphia kind of accent. I was north of Philadelphia, but people don't think they talk with an accent. No one thinks they talk with an accent unless other people explain to them. They just think that they talk normally. Everyone else talks weird, right? And so when I say that I don't think of myself as being strongly affected by the fact that I grew up in Philadelphia, that's completely unfair to the extent that I'm just thinking of suburban Philadelphia as just normal and everyone else is weird, right? That's not true. My notion of what is normal is very much colored by growing up in the suburbs of Philadelphia, going to a large public school, et cetera, et cetera. Sid Huff says, in a talk he gave in advance of the COP26 meeting, Brian Cox argued that while there are plenty of planets elsewhere in our galaxy which could potentially support life, many fewer will have seen life emerge. And such life is very likely to be slime at best. In other words, not conscious sentient life. He then suggested that planet Earth may be the only place in the galaxy supporting sentient life, and he concluded that if life on Earth were destroyed, e.g. by climate change, that would eliminate meaning in our galaxy forever. What do you make of all this, especially the part about eliminating meaning? Well, I think that that scenario he sketches out is one that we should have on the table and take seriously. I wouldn't necessarily attach to it a high degree of credence for a few reasons. There's different parts of it. I think that the least likely part of that scenario is the idea that climate change or some similar catastrophe could literally destroy all life on Earth. I don't think that's the kind of thing that would happen under climate change. It might enormously impact the quality of our life, and I don't want to downplay how bad climate change would be, but a literal, universal extinction level event doesn't seem to me to be the kind of thing that is likely because of climate change. So I think that part of a statement like that is motivated by putting the fear of God into people, right? Which is a perfectly legitimate motivation. We're, if anything, extremely undermotivated to combat climate change. And so making it sound scary is a natural impulse to give into. But the other part of the argument that life elsewhere might be ubiquitous, but might not be highly technological and or even highly conscious and intelligent and complicated, that's harder to judge. It's completely possible. In fact, it's in some sense obviously the simplest explanation for the Fermi paradox, right? Why haven't we found intelligent life elsewhere in the universe? Well, because it's not there. Because intelligent life is super duper rare. That could be either because life is rare or intelligence is rare among life, etc. So something like that is completely plausible to me. The final part, that by eliminating intelligent life on Earth, we would be eliminating meaning in our galaxy or in the universe. I get it. I hear what is being said. I'm not quite sure what to make of that. I mean, I'm sympathetic in general, but I don't have a really clear intellectual argument. It goes back to what we were saying about long-termism and extinction level possibilities, etc. I am certainly in favor of making sure that thinking, experiencing, meaningful life living creatures exist and last for a very long time. I think that's one of the minimal values that it is possible for a human being to have, and I have it, okay? But if I'm honest and someone says, well, why? It's hard to be precise about that. And like I said, I could very easily see an argument that a little bit of meaningful, happy life is better than a lot of miserable life, even if there's meaning in it, right? So that's not to come down on one side of that or the other. It's just to say it's a reasonable question. It's not obvious what the answer is there. So anyway, let's not destroy life on Earth or even make it miserable through climate change. How about that? Paul Hess says, I read that the powerful gravitational waves resulting from black hole mergers cause a reduction in mass. If this mass comes from inside the black holes, would you expect the expelled energy contains information, or would it be another form of the information paradox? So it does not come from inside the black holes. This is Hawking's area theorem. So Stephen Hawking proved that not only if you have one black hole and do things to it, the area of the event horizon always increases, but also if you have two black holes and combine them, the total area of the new one black hole is always greater than or equal to the area of the two previous black holes combined. And the information inside is proportional to the area of the event horizon. That's the famous formula from Hawking and Bekenstein that entropy of the black hole is the area of its event horizon divided by 4 times Newton's constant. So information is not getting out. Whatever information is inside those black holes is still in there. Where the information comes from, it's from the energy elsewhere. Like there's energy in the fact that one black hole is orbiting around the other one, right? That has energy in it. If you had 2 black holes and just really slowly moved them into each other, no energy would be released, but also no gravitational waves either. If you dropped 2 black holes into each other, they would speed up as they came in together, right? And then there would be gravitational waves. But that's where the gravitational wave energy comes from. It comes from the motion of the black holes, not from inside them. Brendan says, sports question. What is your perspective on GOAT? Greatest of all time discussions in the realm of sports such as basketball. My perspective is it's fun but pretty meaningless. I'm definitely of two. I think there are 2 important facts you have to keep in mind. One is that you can't compare people across eras, right? I mean, this is something that has been said many, many times, but it still remains true, and people are going to do it anyway. You just cannot compare Shaquille O'Neal to Wilt Chamberlain. They live in different eras. They were trained in different ways. They played different games. There was no 3-point line when Wilt Chamberlain played, et cetera, et cetera. The league was much smaller when Chamberlain played. It's just impossible kind of comparison. You can't even compare Michael Jordan to Wilt Chamberlain by any sort of traditional impact on the game metrics. Wilt Chamberlain was definitely the GOAT, but maybe he didn't win as many rings as other people did. So, there's different criteria you can use, and you can pick and choose which criteria you want to care about most and get completely different answers, which should be a reminder that there's no unique way to do this. The other point to keep in mind is I do think that at the end of the day, even though this is obvious and trivial, it's worth saying, if what you're talking about is sports, what matters is who wins the game. That's what matters, right? I mean, that's what matters to happiness or whatever. And so the perspective I have on this comes from having been a first-year student at Villanova, that when they won the national basketball championship, the NCAA college basketball championship, and they played in a famous game against Georgetown in the finals. And for those of you who were not there or, were too young or whatever, or don't care about basketball, at the time, that year, 1985, Georgetown was this absolutely overwhelmingly dominant basketball team. They had won the championship the year before. Patrick Ewing was the center, and he was considered the best college basketball player. And Villanova was nobody. I mean, they were ranked like number 20th in the country or something like that. They had a sort of Cinderella run to the championship. They had lost to Georgetown earlier in the year. No one gave them a chance. And then Villanova, in the game, they played out of their minds. They made every shot they took, and they won by 2 points. It was, in consensus, one of the biggest upsets and most fun final games in the history of the NCAA basketball tournament. Too bad you weren't there. That's all I can say. It was a good time to be a Villanova basketball student. But what made me think of it is the center for Villanova at the time was named Ed Pickney. Pretty decent basketball player. You know, he went on to play in the pros for a few years. And Patrick Ewing, of course, went on to have a Hall of Fame career in the NBA. And they actually became friends. So they were rivals in college, but they became friends. And Patrick Ewing at one point said, yeah, I convinced Ed that really our team was the better one, even though they won the game. And, you know, I think that Ed Pickney gave up on that argument too quickly. Like, what does that mean? Greatest, better. Who cares? That's like a completely hypothetical thing. What matters is who won the game. That's what matters. And the point is that Wilt Chamberlain will never play a game against Shaquille O'Neal. There's no win or loss record. Bill Russell might not have been as talented a basketball player as Wilt Chamberlain was, but his team won more championships. And, you know, Wilt did win a couple times the NBA championship, and that counts. And Russell won more, and you know, but who cares? Like it's not even an accumulation. It's like who won that year, right? There's a famous quote. If this was the greatest, what was? Oh, I'm going to forget exactly the quote. You know, if this was the most important game, how come they're playing it again next year? Every year there'll be a new champion. So I think that's what matters. Who won that year? Who won the championship? Who won the game that you're watching? I would enjoy that rather than playing these intellectual games about who is better of all time. That's my perspective. That's kind of a downer perspective. Sorry about that. It's still fun to argue about. P. Walder says, in the recent Clubhouse discussion with Philip Goff, you explained that adoption of a panpsychist view of reality would require a complete reworking of our best understanding of laws of physics. Goff required by saying that his version of panpsychism did not postulate any new properties, as he was suggesting that the charge and spin properties of particles was consciousness. This part of the discussion wasn't continued, so could you explain why this account of panpsychism fails? So, yeah, I did not claim that. I know that Philip claimed I claimed that, but that's not what I claimed. What I said, I do really try to be clear about this, but somehow what I say does not get communicated into other people's brains very effectively. So I'm going to try again. I'm not saying that panpsychism entails that you change the laws of physics. What I'm saying is that if you want to be panpsychist, you have a choice. There's a dilemma, and there are two horns of the dilemma, and you're on one of them. Okay, one of the horns of the dilemma is you change the known laws of physics. You alter with the core theory. You imagine that some other element of reality is somehow affecting the motions of particles to push them away from what they would do according to the known laws of physics. Okay, that is one possibility. But there's another possibility, which is that you invent something panpsychist, some version of reality in which consciousness plays a fundamental role without changing any of the behavior predicted by the laws of physics. That's the other whole horn of the dilemma. So you cannot wriggle out of the dilemma by saying, well, I'd take the other horn. Because the problem with the other horn is the zombie problem. You know, like I said, I think I said this in the discussion. By the way, I'm appearing on Philip's podcast. Philip Goff has a podcast. Philip was, of course, a guest on Mindscape, where I try to, as usual, to let him have most of the talking. But he has a podcast with Keith Frankish, and Philip is pro-panpsychist, and Keith is a philosopher who is anti-panpsychist. So I'm going to appear on their podcast, and that should be available soon. But anyway, the original version of the paper that I wrote, to which Philip was responding, was called The Zombie Argument for Physicalism. And it entirely focused on this horn of the dilemma, the horn where you say, I don't change the laws of physics. But I rewrote it because I realized other people had already said it, and they said it better than me. In particular, Kati Balog, who is a philosopher at Rutgers Newark, I think. But she's written very, very good papers explaining this point of view. And the point of view is the following. Look, the zombie argument says, imagine a world, which I claim is conceivable, where it's exactly the same physical behavior as our world, but there's no consciousness, right? So there can be people called zombies that live in this world that act exactly as we do, but they don't have really conscious experiences, okay? And the zombie argument, as formulated by David Chalmers, another previous Mindscape guest, says, if that's possible, if it's possible to conceive of possible worlds, not our world, but a different possible world where all the behavior is exactly the same, but consciousness is absent, then consciousness can't be physical because I have two worlds, both of which are physically exactly the same, but one of which has consciousness and one of which doesn't, okay? So here's my response to that. Let's say that the short response is to deny the premise that zombies are conceivable. That you think you can conceive of zombies, but I claim you really can't. And here's the reason why, the longer reason. What you're imagining is a person who acts exactly like me but doesn't have that inner conscious experience, okay? But I think that they're not really taking seriously enough the idea of exactly the same as me, behaving in exactly the same way, okay? Because what that means is that a zombie would say they were conscious. A zombie, if there was a zombie David Chalmers, that zombie David Chalmers would invent the zombie argument in favor of non-physicalism of consciousness. If there were a zombie Philip Goff would write a book in favor of panpsychism because that's a behavior. If someone says, I am experiencing the redness of red, or I am in love, or I am sad, that statement they are making is a behavior. So what that means is, if you can conceive of zombies, the zombies are reporting what they take to be their innermost experiences, right? I mean, the zombies aren't lying to you any more than a regular person is lying to you. When a zombie says, I am experiencing the redness of red, they think they're experiencing the redness of red. Why would it be anything else? That's a natural meaning given to the word thinking. So the point is that your evidence for the non-physical nature of consciousness came from your own personal introspection, from the fact that you experience something that you don't think can be explained by the purely physical behavior of matter. But the zombie thought experiment provides excellent evidence that if zombies are conceivable, then introspection is entirely unreliable. Because the zombies are reporting their results of introspection also, and they're completely wrong because they're saying that they're conscious and they're not. So what this really gets down to is the fact that the kind of consciousness that is purportedly being explained by panpsychism, if you don't change the laws of physics, is a kind of consciousness that has no effect on behavior. A kind of consciousness that is completely unrelated to what we talk about when we talk about consciousness, because our talking is a behavior. Our talking obeys the laws of physics, right? And if that's what you're explaining, if you're explaining something that literally cannot be reported on, talked about, or have any influence on how we behave, then I don't think you're explaining consciousness at all. What kind of consciousness is it that has no effect on my behavior at all? That's not what I think of when I think of consciousness anyway. That's what I meant by that horn of the dilemma. But I downgraded it in the paper I wrote because Balog and others have talked about it better than I did. You can read the paper. Consciousness and the Laws of Physics is my paper, and I cite these other people who talk about it if you want more details and a more nuanced philosophical argument than I just gave you. Casey says, I'm curious about the state of cosmic inflation in 2021. It seems like 10 or 15 years ago it was the thing, but I haven't heard it come up much recently. Is it still a leading idea for explaining the early rapid expansion of the universe? Where do you stand on it these days? Yeah, I don't think its status has changed that much, which doesn't mean it's wrong, by the way. Like, a lot of people have implicitly or explicitly this idea that if an idea has been around a long time and it's not been proven right or wrong, it must be wrong because it hasn't been proven right or wrong. That's not how ideas work, right? This is a feature of modern physics, like it or not, that we just have to learn to deal with, which is that our theories that we have and have experimentally tested work. They fit the data. So by construction, the theories that we have that have not yet been tested, like inflation, like supersymmetry or whatever, they're just not being tested by the data. And so we just don't know. And it's really, really, really hard to test them. And it might take a long time. It might even not happen. It might very well not happen in our lifetimes. Let's put it that way. Anyway, there was a brief moment several years ago when we thought that the BICEP 2 telescope might have seen evidence for inflation. People got very excited about that. It turned out to be wrong. It turned out to be a misanalysis of the data. More recently, the BICEP 3 experiment came along, and they actually put even tighter constraints on inflation than we had before, but there's still plenty of room for inflation to be there. So I would say that inflation in 2021 is still the leading idea that we have about the early universe, and in most particularly about the origin of structure, the origin of the fluctuations that grow into galaxies, etc. But we have no more direct evidence for it than we had in 1998 or something like that. I say 1998 because that's when we found the dark energy, the acceleration of the universe that made the universe flat as inflation predicted. That was the last major thing. There's a tiny bit of evidence for inflation that has subsequently come up because, we talked before about scale-free phenomena, things that more or less the same size on every scale. Well, the perturbations in cosmology are an example. The perturbations we see in cosmology are roughly speaking scale-free. They're about the same amplitude at every length scale. And that's a very simple natural thing in some ways. So if you didn't know where something came from, but it was scale-free, you might feel like you were in trouble because there's too many ways to explain it, okay? But inflation came along, and it wasn't even trying to explain scale-free perturbations. It was realized a couple of years after it came along that it did predict scale-free perturbations. But even better than that, inflation predicted that the perturbations would be not quite scale-free, okay? It predicted the perturbations to be, if I'm getting the sign right, a little bit larger on small scales than on larger scales. And no, I think I got that wrong. A little bit larger on larger scales than on smaller scales. The inflaton is rolling down its potential, so the perturbations are getting smaller at later times and therefore smaller scales. So what inflation actually predicts is almost but not quite scale-free perturbations. And that is exactly what we observe. We observe perturbations that are almost scale-free, but not quite. They're tilted a little bit exactly as inflation would naturally predict. That's weak evidence, but it's still evidence. It should increase your credence in inflation just a little bit. I think that inflation has real conceptual issues that it has to deal with. Why did inflation start in the first place, roughly speaking? Was there a sufficiently low entropy starting point that inflation got off the ground? But the fact that it has an issue to deal with doesn't mean it can't deal with it. I just think that that's something where inflationary cosmologists should be very, very worried about this. And it's annoying to me that they're not, but okay, maybe they will get there someday. Per Magnuson says, in the episode with Nigel Goldenfeld, you talk about the scale-free behavior of many different systems. There you go. Is there a connection between this scale-freeness in vastly different systems and the 1 over F noise we also observe in an impressive number of seemingly completely unrelated systems? Short answer is I don't know. I'm answering this question not because I have any wisdom to impart whatsoever, but I think it's a good connection to draw, just so people know about it. I mean, there's this idea of 1 over F noise, 1 over frequency. So that's a power law, right? And power laws are associated with scale-free behavior. So maybe there is some connection, but I think 1 over F noise is sufficiently common, and like you say, in so many unrelated systems, I don't necessarily want to connect it to the same kind of origins of scale-free behavior that Nigel was talking about, because that was very specifically in the context of critical phenomena, where there was some phase transition where you're poised at the point of the phase transition. I don't want to attribute that explanation necessarily to this completely universal phenomenon, but maybe it's there. I don't know. Tom says, in your interview with Stephen Wolfram, you ask him, there's an understanding in traditional quantum computing that there are some problems for which quantum mechanics certainly gives you a speed up. Are you saying that's not true in your model? And he replies, yeah, I think it's not going to be true. That's my guess. I've seen other people say that they don't think quantum computing will work from a theoretical standpoint, even recently. Have those working on it practically not shown it to work yet? Is it still possible quantum computing doesn't work at all? It's certainly not possible that quantum computing doesn't work at all because it works. It's been done, okay? In fact, you can go visit, I think we mentioned this in the podcast with John Preskill, you can visit the IBM Quantum Experience, at least I think it was there. That was a website that used to exist where you can run an algorithm on a quantum computer with a small number of qubits. Go ahead and do it, and it will give you the answer, whatever probabilistic answer appears from your algorithm. That is not a demonstration that you have sped up versus some classical algorithm. In fact, it's the other way around. The actual 6 qubits or whatever they have work more slowly than a classical simulation of it, and it's much faster to run the classical simulation of it. But as you scale up, you might very well hit places where quantum algorithms are faster. Personally, I think it's extremely unlikely that there is some modification of quantum mechanics that prevents quantum computers from working. I don't even know what that would look like. So I don't know. So if Stephen Wolfram wants to predict it, that's the kind of prediction I would encourage people like him to make way more precise, because you can be that. I mean, that would be the gold standard. Like, that's a prediction you could make that is testable and would show that you're right and quantum mechanics is wrong, and Nobel Prizes would rain down on your head if you did that. So that's what I would be working on if I actually thought that was a plausible thing. Regular epistivist says, I need to hear your stance on the anthropic principle. Technically not a question, but that's okay. We'll give it a shot. There's obviously there's different levels of anthropic principle. There's sort of crazy levels where you say the world exists so that we can be here. I give approximately zero credence to that version of the anthropic principle. There is a super obviously true version of the anthropic principle that says, given the universe in which we live, there's a selection effect that says that we human beings are going to find ourselves in the parts of the universe where we can possibly exist, right? I mean, here we are in the solar system on the surface of the Earth. We do not live on the surface of the sun. Isn't that weird? There's a lot more surface area on the sun. There's a lot more cubic volume in empty space than here on the surface of the Earth. Is this a weird, bizarre, inexplicable thing? No, it is not. Why? Because of the anthropic principle, because there's a selection effect, because intelligent living creatures are more likely to be found in hospitable environments than inhospitable ones. That's a completely trivial, inarguable version of the anthropic principle. There's an in-between version, which is, again, trivially true if the conditions are met, which is that if there are regions of the universe where physical conditions are wildly different, so not just the difference between the sun and the earth, but different laws of physics, right? Different, mass of the electron or whatever. If those different regions exist, then again, there can be a selection effect. It may be that in certain regions, living intelligent creatures are more likely to arise than in other ones. And again, you would predict on the basis of very trivial reasoning that we're going to find ourselves in the regime where we can be existing, okay? Now, that's not trivial, even though the reasoning is trivial. The result is not, because it tells you something about the explanatory power of your theories of the universe. The classic example is the cosmological constant, the vacuum energy, okay? Here are two different attitudes one can have towards the cosmological constant. What attitude is, well, there's a multiverse. The values of the cosmological constant are different from place to place in the multiverse. If it's very large, either very large and positive or very large and negative, then there's basically speaking no time for intelligent beings to exist. Therefore, there's an anthropic selection effect, and intelligent beings will find themselves in regions where the cosmological constant is small. Lo and behold, we find ourselves in a region where the cosmological constant is small. Okay, that's it. That's an attitude. Another attitude is there exists a predictive theory that explains why the cosmological constant is small once and for all. Okay, there is a unique value it can have. It is predictable in terms of other constants of nature, and it's the only value it could have had. And we don't yet know what that theory is, right? That's another attitude you could have. So the point is, the anthropic principle, the reasoning in the first example is 100% valid. Makes sense, but we don't know whether the antecedent is true. We don't know if there is a multiverse out there. So even though the reasoning is solid, we don't know if it's the correct reasoning for our universe. But it could be, if we somehow knew that it was, we would stop looking for this predictive theory. Right? If we knew there were different values of the cosmological constant in different regions of space, you would not spend your valuable research time looking for a theory that predicted a unique value, because you knew it couldn't be right. So that's why so I'm not saying which is right and which is wrong. Right now, since we don't know, it's worth exploring both alternatives. But it's certainly not worth saying you can't take seriously the idea there's a multiverse and invoke the anthropic principle because we can't see the other universes. So therefore, it's not science. That's a completely bizarre point of view to have. Even if we can't see the other universes, whether or not that scenario is true is a perfectly physical, sensible question about the universe. And it's a question that affects the way that we think about the universe, that affects the models that we do build. So we have to take that possibility into consideration. I don't think it's in any sense settled that it's the right way of thinking about the cosmological constant, but it's absolutely on the table. Okay, I think we're down to just two last questions. Dominic Adam Jones says, when applying Bayesian reasoning to questions like whether it rained last night, all seems to work fine. However, when applying it to scientific theories, it seems more problematic. Given we can be pretty sure none of our current theories is 100% correct, it seems that we should apply low credences to all current theories, but that doesn't seem to correspond to how we behave nor how we feel. So this is an excellent question, but I think there is a resolution. I think there is an answer. This is one of those times when I say it's an excellent question because I know the answer. Sure, none of our current theories is 100% correct, but a good theory won't be 100% wrong either. Sometimes theories are 100% wrong. If you go back to the 19th century, there were theories of the phlogiston theory of combustion or something like that, or the plum pudding model of the atom, which were just wrong, right? Or the geocentric model of the solar system. But a good theory, a better theory, will be somewhat correct, will capture some true behavior of the universe. Newtonian mechanics or Newtonian gravity does capture something true about the universe. It could be rigorously derived as a limit of general relativity or special relativity or quantum mechanics, right? So the interesting thing is that when you go from, classical to quantum is the best example, but even when you go from Newtonian spacetime to relativistic spacetime, your ontology changes, right? Your fundamental way that you describe reality changes. But as we talked about with James Ladyman, the philosopher, a long time ago, there's something that is preserved even in those transitions, some structural thing, some relationship between different parts of the theory. So when we say things like, the standard model of particle physics is correct, it's not, as you say, 100% correct. It will give out. It will have some domain of applicability, but it will never entirely go away. When I say that the table in front of me is made of atoms and the atoms have in them electrons, protons, and neutrons, that will never stop being true. Even if we learn that electrons and protons and neutrons are made of other things and that space-time is made of other things and it's all just a wave function or all just bits or something like that, there will always be a level of description on which it is correct to say the table is made of atoms, and those atoms are made of electrons, protons, and neutrons. So I think that's a perfectly legitimate attitude to have towards scientific theories. The good ones capture something true that is never going to go away. Final question is from Kyle Stevens, who says, in your recent episode with David Wallace, David states on the topic of Boltzmann brains and the infinite, if the universe is such that it predicts that it's full of beings who have fake histories, there is some reason to worry that the theory is self-undermining. Do you hold this same concern? Should we assign some credence to the possibility that we ourselves are simply Boltzmann brains? So yes, I do hold the same concern. In fact, this concern was largely my fault. It was articulated by me in a paper called Why Boltzmann Brains Are Bad. And so I'm letting David talk, but he's basically quoting me. I'm sure that other people had rough ideas that were similar. I don't want to claim too much originality there, but I think that I did put it in very clear, definitive words for one of the first people to do that, if not the first person to do that. And the basic idea is, the traditional way that physicists think about the Boltzmann brain problem, if they think it's a problem, is that they say, if you have a cosmological model that predicts that most people like us are Boltzmann brains, then I should be a Boltzmann brain, and I'm not, therefore the theory is ruled out by data. Okay. So I think that's entirely bogus, that reasoning, and I've had arguments with people about this. But as I said before, when we were talking about me versus Sir Isaac Newton, there's zero credence that secretly I should have been or could have been or would have been Isaac Newton. I'm me. Isaac Newton is Isaac Newton. I'm not a Boltzmann brain. So I'm me. Let's put it that way. Whatever I am, whether I'm not a Boltzmann brain, I am not a brain floating out in empty space, because that would have very different experiences than I'm having. Even if most of the intelligent beings in the universe were brains floating out in empty space. I am clearly not one of them, okay? That does not rule out the theory, because in that theory, there's also a lot of people who are not brains floating out in empty space. And the relative numbers don't matter. I'm someone who believes that when you do these anthropic reasonings, you're allowed to take into account the data you have. And the data I have already tells me I'm not a Boltzmann brain, so I can't be re-surprised by that fact when I look around and I notice it, okay? So that's not the evidence against the universe dominated by Boltzmann brains. The evidence against that kind of universe is that even when I take into account all of the data I have, even when I say, oh, look, here I'm in a room and there are tables and I feel a gravitational field under my feet, there's clearly a big Earth-like thing beneath me, I believe that outside there's something called the city of Boston, etc. Even when I conditionalize on all that, in a universe that is dominated by random fluctuations, zero of my beliefs about the outside world are likely to be true. Even though I believe I'm in a state called Massachusetts, there's almost no chance that that's actually correct, right? It is far more likely that my belief in the state of Massachusetts randomly fluctuated into my brain than that the entire state of Massachusetts randomly fluctuated into existence, okay? And that's what David Wallace is referring to. The real problem with the Boltzmann brain scenario is not that it's ruled out by data, but that it leads you to conclude that all your beliefs about the world are wrong, including the ones that led you to believe that there's a Boltzmann brain problem. So you cannot simultaneously believe that the universe with random fluctuations is true and that you have good reasons to believe that it is true. That's what it means to be self-undermining. So my solution to that is to just give very, very low credence to cosmological scenarios with all these random fluctuations in them. In other words, the conclusion I reach is roughly speaking exactly the same as someone who says, well, Boltzmann brains just ruled out by the data. Namely that if your cosmological scenario features domination by random fluctuations, then you should throw it out. You should try to do better, build a better cosmological scenario. But my reasoning for getting there is different. And I wanted to talk about this question because there is like one little lingering thread that can be pulled on here, which is not completely settled in my mind, which is that I don't want to give zero credence to the idea that I'm a Boltzmann brain because I don't want to give zero credence to any logically consistent possibility. And the reason is because if you give zero credence to something, then literally no future information can make you believe it, right? You're multiplying zero by some finite number, you're still going to get zero in Bayes' formula. So you always need to be open to the possibility that new information will come in that will change your mind. So every possibility should have some non-zero credence, but it should be very, very small. And so we get back into this question of what do we do with really, really, really unlikely things in the universe, whether it's branches of the wave function, existential risks, or what have you. I'm not sure we have a really well-developed theory for dealing with these kinds of things. So my current attitude is just say no to Boltzmann brain cosmologies, and if evidence comes in that it's a better fit than what I think, then I'll update accordingly. But it won't be a formal Bayesian updating. It'll be, a fuzziness becoming a little bit clearer. That's something we can all aim for. Fuzziness becoming a little bit clearer. Something to aspire toward. So happy Halloween, everybody. It's Halloween 2021. November is coming. Talk to you soon. Thanks for your support for the Mindscape podcast. Keep listening. Tell your friends. Bye-bye.